Hello, madam. Is it audible? Hello.
నమస్కారం అండి.
Namaste, namaste, namaste. Archana, madam, is it audible? Sneha says?
Yes, sir.
Okay. Now, are you allowing the participants also?
Yes, sir. They're allowed.
There are how many are there? Any participants joined?
Yes, sir. Participants already have joined, sir.
Joined, huh?
Yes, sir. Just now, we informed to our first resource person, Dr. Sanjay sir also informed, sir.
Uh-huh. Today's main two Sanjay Kumar Patra.
Sir,
To be,
good evening, Baba, sir.
నమస్తే.
Hmm.
నమస్తే.
Sanjay Kumar, what about Sanjay Kumar Patra, sir?
Sir, he is about to join.
Uh-huh. Okay. Today main is these two important resource persons
Yes, sir. Yes, sir.
and our VC and principal. Principal, what about principal, sir?
Sir, just now he was there.
Mm-hmm. Snazes, you have to control all the mic, okay? Mute everyone because
Yes, yes.
the participants may try to open up and talk something, no? So you have the power to control all the participants, okay?
Yes.
Okay.
ఎస్ నేను ఈరోజు వెళ్ళదమ్మా, ఈరోజు మీటింగ్ ఉంది రాత్రి 9:30 వరకు.
Hello. Hello.
Archana madam,
Yes, sir.
VC sir joined and all our dignitaries almost joined.
Sir.
We can start at exactly by 6 o'clock because our inauguration is from 6 to 6:30.
Yes, sir.
Remaining people, all the participants will join slowly one by one.
Okay, sir. Snazzy, sir.
Very good evening, sir.
Good evening to one and all present here. It gives me immense pleasure to extend a heartfelt welcome to the dignitaries, the Honorable Vice Chairman of the MITS Group, Sri Viswajit Panda sir, the Director of MITS Rayagada, Dr. C.V. Gopinath sir, and the Principal of MITS Rayagada, Professor Ramanuj Naik sir. A special welcome also to all our respected resource persons from various prestigious institutions and industries across India and abroad, and the participants who have joined us for this important program. I am Ms. Archana Anand, Head of the Civil Engineering Department and Coordinator of this ATAL FDP. Along with my co-coordinator, Ms. Shivani Janna, we are thrilled to welcome you all to this faculty development program on next generation sustainable materials for eco-friendly and durable civil engineering structures. This program is a wonderful opportunity for us to learn, collaborate, and explore the future of our field. The knowledge and insights shared here will undoubtedly contribute to a more sustainable and resilient structures. To officially begin our program, I now request our Honorable Vice Chairman, sir, to inaugurate the FDP by lighting the ceremonial digital lamp and address the gathering with his inspiring words. So,
कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते सम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः
Good evening, everyone. My heartfelt namaste to everyone. It gives me immense pleasure to extend a warm and heartfelt welcome on behalf of MITS Rayagada. Each one of you to this faculty development program on next generation sustainable material for eco-friendly and durable civil engineering structure. We are honored to host this FDP, sponsored and supported by AICTE at a time where this global focus is rapidly shifting towards sustainability, resilience, and innovation in infrastructure. We all know the infrastructure requirement is changing day by day. The things are getting evolved on a daily basis, like the infrastructure, the materials which you're using is evolving. I think as all civil engineers and academicians and researchers, you all play a vital role in shaping the environment, not only today, for the next generations to come. We all know that the construction industry is going on a rapid transformation, driven by the urgent needs, like to address varieties of issues like climate change, reduction of carbon footprints, to promote sustainable development. So the reason we chose this topic for this FDP, just to see that, like, to have a platform where we all can exchange ideas and educate ourselves and expose ourselves in terms of rethinking using of traditional material or using of eco-friendly alternatives that they're not only sustainable but also durable and cost effective. That's the main aim of the FDP, which when you're in a conceptual stage, when you've thought of what will be the topic of the FDP. And I'm very happy to see the resource person, like the eminent experts, the industrial profession, the academician who has consented us to be part of this FDP. I believe that the pool of resource person we all are having, like part of the FDP, will help us to get more and more knowledge, information, and exchange of ideas, so that the outcome of the FDP will be achieved what we have thought of. And we believe this program will serve as a valuable platform for knowledge center and skill enhancement and collaborative learning. I sincerely thank to the organizing team, the director of MITS Rayagada, Dr. C.V. Gopinath, the Department of Civil Engineering headed by Archana Anand, and their team member, Snehasis, Surlin Raut, and other faculty member. I extend my sincere and special thanks to the guests, resource person, and the participants of being so active, and all are present during the inauguration session. Definitely your presence and engagement will undoubtedly make this program a meaningful and impactful one. I believe that we will all work together and will learn in this entire week FDP program, and we will be probably end of the week, we will be having a better, cleaner view in terms of using of more durables and eco-friendly materials for civil engineering structures. Once again, a very warm welcome to all of you, and wish you a productive and inspiring week ahead. Thank you everyone for hosting, accept our FDP, all the guests giving the consent, and I will definitely believe that your participation will make this FDP more fruitful and the outcome will be much more sustainable, what I believe. Thank you everyone.
Thank you.
Thank you, sir. Thank you so much for your valuable words. Next, I request our respected director, sir, Dr. C.V. Gopinath, sir, to kindly say a few words and share his valuable insight with us.
Thank you, Professor Archana Anand. Thank you for giving this opportunity. First of all, Very good evening to all the learned members and the participants of this program. First, let me welcome our Honorable Vice Chairman, Mr. Biswajit Panda of MITS Group, Rayagada and Bhubaneswar. My colleague, Professor Ramanujan Naik, Head of the Department, Archana Anand, and coordinator of this program also, and Dr. Surilin Raut, and Shivani Jana, Snayasi Sahani, and all the learned resource persons, particularly from the faculties, from the academia and industry. First of all, let me thank the AICTE for giving us this wonderful opportunity and platform to share our knowledge to the fellow colleagues, entire learned faculty across India. As already our Vice Chairman told, a lot of deep discussion happened while choosing this topic. And nowadays, all of you know that India emerging in so many areas, particularly in infrastructure also. In infrastructure, the United Nations already gave certain goals, sustainable materials particularly. So the topic of this FDP is sustainable materials for eco-friendly and durable civil engineering structures. So we applied this, ensuring that new outcome will come, new thought process will be there from learned members from academia and industry practicing engineers. Almost more than 50% of resource persons are from industry. And those are from Adani, Navayuga Constructions, Aman Dastur and Company, and many of them from government manufacturing companies also. So I'm really thankful to all of them when we announced this program and persuaded them to be part of this program, and they came forward, and I'm thankful to all the members. I'm also thankful to my batchmates. I think I'm really thankful to Mr. Ramesh Mova, and S. Ramesh, and Gunakar, and from Adani Ports, Adani Airports, and my colleagues, ex-colleagues like Professor B.S. Verma, B. Srinivas Verma sir, and from faculty who are from abroad, Afzal Khan sir, and all these members. Actually, a lot of enthusiasm is there to share their knowledge to the fellow colleagues. And this wonderful opportunity, wonderful platform where we can sit at our homes and our offices and share this knowledge. I'm really thankful to AICTE for creating this ATAL platform to share this knowledge. I'm really thankful to all the faculty coordinators who worked day and night for last 6 months to prepare this program and getting this confirmed from the AICTE. Once they confirm and contacting these people, and we are very, very much thankful to the participants. 159 registered participants are there. Slowly they are coming now. It is 79, it is showing 75 members. So I think they may be adding by 6:30 p.m. when the first session starts. And all of you know that I'm telling you once again, all of you are from academia. You know what is ATAL. Minimum 80% marks are required after the program. We will conduct one technical quiz at the end of the session, means after Saturday. The 13th session is over. We will send you one Google link where the questionnaire will be there, multiple MCQs. So you have to answer, In that, you have to clear that and you have to get 80%. And at the same time, Monday to Saturday, 13 sessions will be there, and you have to attend minimum 70%. So without 80% of marks or without 70% of attendance, you will not be eligible to get the certificate. So definitely, we will try our best to be interactive and share our best knowledge to you. Please attend regularly and participate with the faculty members. Interactive sessions will be there. You can answer. This is a online mode. If you have any question, please don't ask immediately because it will be disturbing to others. So there is a chat box. You can give the question, and our coordinator and co-coordinator will be going through the chat box and share the questions to the resource persons, and the resource persons will immediately answer you. At the end of the session, there is a question and answer session is there. So 1.5 hour session. So definitely 1 hour 15 minutes will be the program. The last 15 minutes will be question and answer sessions will be there. You can please put your question on the chat box. So our coordinator and co-coordinator and the fellow faculty members who are going through that, and let us not disturb the resource person while going through the program. Definitely. And I'm really thankful to my participants because these participants are from across the country. I'm really thankful from Aizawl to Ahmedabad, Kashmir to Kanyakumari, Kerala, Mizoram, all, and each and every state are covered. I have gone through the 159 participants. I'm really thankful to all the participants. Definitely, we try our best to do our sharing the knowledge. If any problems are there, please share with us. Our team is ready with us, ready to solve immediately. And my sincere request is don't unmute your mic and talk to each other such that it will be disturbing to the resource person. Okay. So thank you one and all. All the best. Wish you all the best. You can carry.
Thank you, sir. Thank you so much for your valuable thoughts and words. I now invite Dr. Surilin Raut Madam to present a brief report on the ATAL FDP development program, outlining the objectives, themes, and schedule of these enriching events.
Thank you very much, ma'am. Thank you very much, ma'am. I, Dr. Suryalin Raut, am very much glad to have the opportunity to brief you about the ATAL AICTE FDP. With immense pleasure, we express our sincere gratitude to AICTE for shortlisting our proposed topic for the ATAL Faculty Development Program to be conducted by our institution in online mode. The selected topic, like next generation sustainable material in civil engineering construction, was chosen in light of its increasing relevance and importance in modern construction practices. As the civil engineering community places a great emphasis on minimizing environmental impact, it becomes imperative to educate faculty and other professionals about sustainable alternatives such as geopolymer concrete, recycled aggregates, and bio-based materials. So at very first beginning, we experts with strong academic and industry experience in sustainable construction materials were identified. Then a formal email was sent outlining the goals of the FDP, the proposed topic, and the expected learning outcome. Next, a follow-up mail or call was made to confirm the availability of the selected expert and discuss session plan in details. The resource person shared their presentation materials and suggested key focus areas such as life cycle analysis and performance evaluation of sustainable materials. Our FDP session covered a series of interactive lectures like properties of emerging sustainable materials, case studies of environmentally conscious infrastructure project, practical demonstration, and strategy for implementation. We currently have 150 participants registered for the ATAL FDP. This indicates a strong interest in the topic among the participants. We hope attendees will actively participate in discussions, raising valuable questions about integrating these concepts into academic curricula and practical application. Participants will provide feedback regarding the effectiveness of the FDP in enhancing understanding and teaching of sustainable construction materials. This input will guide us in further refining our approach and curriculum. We are very much optimistic that with everyone's effort and cooperation, this program will be a grand success. Once again, we thank AICTE, our all resource persons, and all participants for their support. Thank you.
Thank you, ma'am, for your valuable time and efforts. Following this, I request our beloved principal, sir, Professor Ramanuj Naik, sir, to kindly deliver the vote of thanks, acknowledging the efforts and contribution of everyone involved in making this FDP possible.
Good evening to everyone present. On behalf of Majhighariani Institute of Technology and Science, Rayagada, it is my privilege to extend a heartfelt vote of thanks at the inaugural session of this AICTE Training and Learning ATAL Faculty Development Program on Next Generation Sustainable Material for Eco-Friendly and Durable Civil Engineering Structures. First and foremost, I express my sincere gratitude to AICTE and AICTE Academy for granting us the opportunity to host this FDP and for their continuous encouragement towards enhancing faculty competencies in the emerging area. I extend my special thanks to our Honorable Vice Chairman, Sir, resource persons, keynote speakers, Honorable Director, Sir, for sparing their valuable times and sharing their inspiring insights that have truly set the tones for this program. I am deeply thankful to our organizing teams of Civil Engineering Department, headed by Mr. Archananand, whose dedication and meticulous planning have made this event possible in an online mode with such smooth execution. My heartfelt appreciation also goes to all the participants from across the country, around 160 plus, who have joined us today. Your active participation and enthusiasm will surely enrich the learning outcomes of the FDP. Last but not least, I thank all the supporting staffs, technical team, and coordinators for their effort behind the scenes to ensure the success of this inaugural session. With this, I once again thanks to everyone for their valuable presence and contribution. I wish this FDP a great success and hope this session ahead will bring fruitful knowledge and sharing and collaboration. Thank you.
Thank you, sir.
Madam, verify Professor Sanjay Kumar Patra is
Yes,
attending.
sir. Yes, sir. Yes, sir.
Is there?
Yes, sir.
Okay.
Good evening, everyone. It is my privilege to introduce Dr. Sanjay Kumar Patra, Professor in the Department of Civil Engineering and Dean of Academic Affairs at Veer Surendra Shah University of Technology, Bulla. Dr. Patra holds a PhD from IIT Bombay and completed his postdoctoral fellowship at the University of Kansas, USA. He has over 120 research publications, a patent to his credit, and has guided several doctoral and MTech scholars. His expertise spans concrete technology, seismic engineering, structural durability, and applications of machine learning in civil engineering. He has been recognized with prestigious awards, including the Best Faculty Award at AICTE University and VSSUT Bulla, along with several honors from the Institutions of Engineers, India. With vast international exposure and rich academic contributions, Dr. Patra continues to inspire through his research, teaching, and leadership. Finally, I request Professor Sanjay Kumar Patra, sir, please take over and begin the first section of this FDP. Thank you once again for your presence and support.
Sir, still time is there. Actually, 6:30 not at over. Can we wait or we'll start? Sir, Sanjay Kumar, sir? Are you
Yes, sir.
there?
No, we can start if your all participants are ready. Then we can start, sir. No issue.
Okay, sir. So almost 91 are there, sir.
Uh-huh.
91 participants are there right now.
Hmm.
Some people may join because we gave the time 6:30, no? And think, or you can initiate the program, sir. You can start the program slowly.
Okay. Okay.
You can test your screen, sir.
Yeah. That's what I'm doing now.
Yeah, whether it is possible to share your screen.
Yes.
Yeah.
Yes.
Snehasis, you can unshare your screen. Yeah.
Yes, sir.
Now it is touching 100, sir. 100 people are there. Visible, sir, now.
Okay.
Right, sir.
Okay. Should we start, sir?
Yeah. Please, sir, start, sir. Almost touching 100, sir.
Okay. So, respective dignitaries, those who are there in MITS, Rayagada, in particular, Dr. Gopinath and Dr. Suryalin Madam, and all the members of this FDP program, I would like to extend my hearty regards to all of you for giving me an opportunity to deliver the topic what we have proposed today. And also I'd like to express my gratitude to all the participants who has found the topic of interest and also join for this. So here we will move forward with our talk, that's nanotechnology in civil engineering, enhancing material sustainability. So it's a broad term. We all understand it's a very broad term, but what we will try, what I will focus in this 1.5 hour of time, I will give the what exactly happens with the materials what you are using in civil engineering. Whenever you are using this nanotechnology, what kind of improvement happens and what level of fundamental understanding is required whenever you move forward with this. That I will focus. Am I audible, sir?
Yeah, audible, sir. Snehasis, you mute all. Snehasis? Snehasis. Yeah. Sir, you please go ahead, sir.
Yeah. Somewhere I could not able to move my slides. Yeah, it's okay. Moving. Okay. Now let us come to, before we move forward in nanotechnology, let us have some little glimpse about the concrete. See, as we know, concrete is not just cement and not a particular kind of a stone. Concrete is kind of a heterogeneous product, though we assume it is a homogeneous product in our analysis point of view, simplification for simplicity point of view, behavioral point of view, but we do understand it is a mixture of many kind of ingredients. Whenever we say it is a mixture of many kind of ingredients, looking at the size of the ingredient, it moves to a multi-scale material. Whenever it moves to a multi-scale material, that is the beauty of the concrete, why it is so popular, because of its multi-scale nature. Because of multi-scale nature, it is having various kind of sizes and various kind of surface area, which is governing the performance of the concrete. If we very well understand the size of materials what you are using as an ingredient in the concrete, and if you could understand the kind of amount of surface area of each ingredient, then automatically we can have a feel of its performance. When we prepare the concrete, when we manufacture the concrete, then automatically you can understand its performance. Before we move forward to the nano, if I look at the concrete at its conventional state, what do? We use the conventional materials like cement, fine aggregate, coarse aggregate, water, if any sort of superplastic, if necessary. When we do prepare that, then we are getting a hardened concrete in due course of time. If that was there, then what was the necessity of further improvement in the concrete? The necessity came out to improve its performance, to improve its strength. Then why the performance improves, why the strength improves, if you put a question to there, then definitely it comes to be the kind of ingredients what you are adding to the concrete and its specific size and its specific surface area. See, these days, what we realize, we no more use the ordinary Portland cement in our practice, in our construction practice. We are very popular to use the materials like Portland pozzolana cement, Portland slag cement, and in particular fly ash based cement and composition of both fly ash and slag based cement. Why they are popular? The popularity is because of their pozzolanic behavior. As you all understand, if I do look at the cementitious material is having binding property. But when we come to the pozzolanic material directly, it doesn't develop the binding property. But when it comes in contact with any other molecule, with the addition of water, with the addition of any other substances, then it develops the binding property. And when it develops the binding property, that leads to a durable concrete. Sometimes by managing properly, that leads to a high strength concrete, that leads to a high performance concrete. So looking at that, if you look at this plot, what I have shown here, see the coarse aggregate is here the largest size. When we gradually move towards the left and moving to up, then we see in the middle portion of that, we are having the ingredient like fly ash and some kind of other kind of performance. You can look at the silica foam and metakaolin. There are some performance we are adding, and which is very good for the pozzolanic activities. So when they are very good for the pozzolanic activities, that what I say, because of their pozzolanicity, we would able to get its high performance and high strength. But that is the conventional thing, what you have understood and what you know prior to nanotechnology. Now let us come to the nanotechnology. To understand this nanotechnology, here we had a plot of x-axis and y-axis. What is there in x-axis? In x-axis, what we are having, the particle size in millimeter. That's in the scale of millimeter, in the converter to the nanometer. Then y-axis, we are having the specific surface area, that is unit meter square per kg. So when we come to the nanometer, so that unit, I think everybody understands that nano means 10 to the power minus 9. When it's come meter, 10 to the power minus 9 meter, something with that unit, then you can imagine how small it is. So to put proper identification to the scale, we had put everything with the x-axis to y-axis there in the logarithmic scale. Then what do we observe in this logarithmic scale? Whenever you look at plot, when you move towards the right, the y-axis parameter, when you extreme right, if you look at the coarse aggregate, this particle size is high. When you look at its y-axis data, then the specific surface is low. When you move towards the left, when the particle size is small, the specific surface is high. That is the importance of this nanotechnology. See, these small particles, the nano level particles having high surface area. So as you go on reducing the size of the particle, we are getting an enhanced size of surface area. That enhanced surface area, what does it do? If you look at that, it is the extreme high surface area. It is good for reactivity. And not only good for reactivity, it is also used as a filler kind of things and filling the micro voids. But more importantly, the reactivity of the high surface area materials is an important phenomena on use of the nanomaterials. That's why when we bring down the size, we are enhancing the specific surface area. It helps us the better reactivity. So when it helps the better reactivity, then we are getting a hardened product in due course of time. Now look at the middle portion. That is silica fume and metacoiling. They are in the micro. See, if you look at the ranges, the conventional concrete leads to the high strength concrete, leads to nano-engineered concrete. When you lead to nano-engineered concrete, it is leading very high, not only strength, we are getting many other improvement in the performance. It improves the microstructure, it improves the durability, it improves the strength. Then the question may come also, does it not there in the kind of high performance? Is it was there, but it is better than to that. That we will see in the course of slides, what way it can better, what other benefits we are getting out of this using this nanomaterials into our concrete. But here you need to understand, in these three ranges, in a conventional process, that is kind of, we can consider a macro range like the natural sand, coarse aggregate, fines, this can be a macro range. But when you go to the micro range, there we are seeing the silica fume, metacoiling, and fly ash and GGBS, they are the game changer kind of things. And though they help to improve, because their specific surface area may not be very high, may not be very low, it can be a moderate specific surface area. This moderate specific surface area also helps us to get a reactive elements, and also it helps us to improve the performance. That's why we are able to get the high strength, high performance concrete in that zone also. When it comes to the nano-engineered concrete, it improves the strength, durability, and microstructure better than the high strength and high performance concrete. What was at the micro level, better than the your micro level ingredients. So if you look at nano-engineered concrete, it uses very small particles, nano level particles having high surface area. If you look at the high strength concrete and performance concrete, it's micro level, it includes silica fume, metacoiling, and they are helping as a fine particle packing, and it also helps to reduce the porosity. But in conventional concrete, though it is having adequate strength, but it is fails for a more durable concrete because it is having some kind of a porosity inside the concrete. So those porosities are not helping us as a durable concrete. So what is the key takeaway from this? The smaller the particle, the greater the surface area, and the more it can influence the hydration, the reactivity activity, and improve the microstructure and improve the ultimate performance. That's why these nano additives can be a game changer for the concrete. Now, coming to next slide here, if you look at there, we saw the sizes versus specific surface area. Now here we can see in particular what it does it. As you understand, concrete is not uniform. It is a complex structure ranging from the atomic scale to the size of gravel. Each scale requires different observation tools and contributes differently to the performance. If you look at the scale, it is wide range of scale. In this wide range of the scale, starting from the pico scale to the macro scale, starting from the very micrometer to the millimeter, then each substances cannot be observed from the similar kind of observation tool. So if you look at the macro scale, if something is in terms of millimeter, you can see in the naked eye. But something smaller to that, it is not possible to see the naked eye. There you can see the optical microscope. Now these days, the high resolution cameras has come out. With the help of those cameras also, you can able to identify some kind of optical level microscope at the micro level. But again, smaller to that, what we have realized in case of our microstructural analysis, then we require SEM, scanning electron microscope. But scanning electron microscope also have some limitation where it can see the things up to mesoscale and up to the microscale. But when it comes to the scale of nano, when it's called the scale of 10 to the power minus 9 towards below the 100 nanometer, then these equipments, these tools are not good enough to visualize it properly, to understand, to observe the property properly. That's why So different substances at different scales require different observation tools. So when you look at different observation tools, looking from left to right or right to left, see there, if we start with the nano, then we require the equipment like AFM and TEM. What is AFM? It is a atomic force microscopy. And what is TEM? It is transmission electron microscopy. So with the help of atomic force microscopy, what we are able to see, we are able to see, or we are able to measure, we are able to localize many different forces inside the molecules. What kind of forces it develops among the molecules, including their adhesion, including their magnetic forces. All these kind of observations we could be able to quantify with the help of atomic force microscopy. So from that quantification only, we can understand the phenomena of behavior and the behavior phenomena of the nanoparticles inside to the concrete. Similarly, another equipment also there, that is transmission electron microscope. It may not give directly the force quantity, but it will give you, if you, from the picture also you can see it can give you some pictorial two-dimensional view of these molecules or atoms, what are there inside the material or inside the concrete after its a hydration process. So those observations we can quantify using these equipments AFM and TEM. Now when we look at the SCM, there the kind of pozzolanic materials what you are using and the kind of the compounds what it develops in the process of hydration, in all those observations we can see in the process of scanning electron microscope, and the morphology behavior we can quantify in there. Similarly, the optical microscope, further course of things we can observe in the optical microscope with a visible scale, and all the macro measurements we can understand in the naked eye. See, by quantifying these, what it helps us? It helps us to quantify the CSH clusters inside the concrete after use of the nanomaterials, after reaction of the nanomaterials, after use the short-term behavior and long-term behavior. All these things we could able to observe. And all the nanoscale measurements like nano TiO2, nano Al2O3, nano SiO2, that one is nano alumina, nano silica, nano TiO2, titanium oxide, and all those, how it process in the hydration and how it is filling the pores, all these things we could able to quantify with this observation tools. And as it discussed, so we could able to quantify at the nanoscale, microscale, macroscale, but not the same equipment. For the measurement at a different level, we are using the different level of observation tools to quantify that. Then why it is so? If I do observe some, I will observation some of the using the tools, expensive tools, by measuring these quantifications, then what way it helps us? It helps us. It has some relation with its macro property. See, if at the micro level, some pores of, if you look at this pore observation, as per IUPAC classification at the bottom of the plot, see the microscale, mesoscale, and macroscale is less than 2 nanometer. Some gel pores is there, then it is an effect on the shrinkage and creep. If the mesopores are 2 to 50 nanometer, then it has an influence on the permeability. Similarly, in macropores, if because if the size is less than 2 nanometer, we are calling it a micro pores. 2 to 50, we call it a mesopores. Similarly, more than 50, macropores. So these micropores, mesopores, and macropores have some specific influence, like effect of shrinkage, effect of creep, and permeability and mechanical property. All those properties we could able to predict from this observation at the macro level or macro level, nano level. Now, out of this, what do you understand here? Concrete properties are controlled at multiple scales. So nano engineering works because changing things at the smaller scale can greatly improve the large scale performance. So if we do some little kind of arrangement at the nano level, it has a huge impact on the macro level. So that we can realize from its process, from its reactive behavior, and from its performance. Now, let's move to the next. With this introduction to the nano behavior and how they are observed in the tool, we will move to the next part. Now the question may be arised, how can you get these nano size materials? As you all understand, whatever the ingredients we are using in the kind of concrete, other than the chemical admixtures, they all are raw materials are available, like the coarse aggregate, fine aggregate, and the cement, factory made product cement, and some kind of fly ash, silica foam. All of these factory made available to ingredients are there, and we are well conversant with those ingredients, and we collect and do the mix design. Now the question comes, if we are using nano particles into the concrete, you might have some curiosity how they are prepared. That curiosity, let us clear here. There are two ways of approach to prepare those nano particles. One is top-down approach, another is bottom-up approach. What is the top-down approach? In top-down approach, we collect the bulk materials and break them down using the milling, grinding, or any other means. Some kind of grinding technique or milling technique and some breaking technique, some kind of techniques we are used in mechanical forms to bring down the size of the bulk material from a macro scale to the nano scale. Until it reaches to that level of fining, we have to do that grinding, we have to do that milling. That way of doing. What is the example of that top-down approach? The fly ash. So we have a fly ash available from the factory with some specific scale and some micro scale level of things what we have seen in the previous graph. Those things by milling and grinding, we can bring down fly ash to the nano fly ash form. The fly ash in its raw form, when you use in the concrete, when you bring down the nano fly ash, we will use in the concrete, it will have quite different behavior on its performance because of its specific surface area and because of its size and because of its molecular behavior and molecular positions. And those things we can do, prepare the nano fly ash from the top-down approach. Similarly, what is bottom-up approach? In bottom-up approach, we start from atoms or molecules. We take specific atoms. From selected atoms, we prepare a molecule. Like the molecule what you have seen in just the previous, we will see in move further also. The molecules like your nano silica, nano alumina, nano titanium oxide, nano ferrous oxide. Like these nano things, when you look into that, what they are assembled. We are assembling the atoms and molecules. How we are assembling? By using some specific approach, that is Sol-Gel synthesis or other some synthesis or what other synthesis are proposed. Then we are making them or letting them chemically self-assemble into nanoparticles. So these things we have to do in the control laboratory environment. So that's why these two things what we discussed here. One is the top-down approach, existing material we will grinding in to bring into the nano form. Another by assembling the atoms and molecules to develop a nanoparticle. That is the bottom-up approach. This two way what we can make. Now let us see. Out of different nanoparticles, let us look at one-to-one nanoparticles, how they are behaving with the cement. See, as you all understand, in the concrete, kind of coarse aggregate and fine aggregate, they are there just to fill the physical spaces. But who is the main material which is helping us to unite the concrete as a single unit? That is the cement. So why it is uniting into a single unit? Because cement is a cementitious property. These cementitious properties has a greater role, as a binding role, which is uniting to put it a single behavior of the concrete. So then in that cement, which kind of things are developing, which is helping us to do that? That is the CSS gel. All you have understand. So in the process of understanding concrete technology, everybody is very familiar with the terminology CSS gel. Now here, this nano material, the nano additive, what you are adding to the concrete, that is having a major role, the behavior, the interaction between CSS gel to the nano product. That is matter to understand clearly here. See here, If you don't use the nanomaterial, what it does, in the process of hydration, the concrete or the cement produces CSS gel and CH gels, calcium hydroxide and CSS gel. These things, when it is develops at early process of hydration, the inner CHH formation is slow and less dense. That you can see from the graph, from the plots here. See, if you look at the plot, the early hydration of pure cement in the plot A, there is a division A and B. If you look at the A, the top part of the figure, if you look at in the process of hydration, the inner CHH, what it is there, its formation is slow and it's less dense. And surrounding to that, there are some calcium hydroxides there. After the outer CSS gel, there are some calcium hydroxide is there. But what it helps with nanosilica, when you add nanosilica to there, nanosilica particles act as a nucleation sites. What is nucleation site? See, nucleation site is nothing but it is a step in forming a new phase or a structure, new frame of phase and new frame of structure, such as atoms or ions or molecules. They aggregate, they combine, they assemble to a stable form and self-organized nucleus form. So this thing, as usual, it doesn't happen, but when the nanosilica particles are to there, it accelerates that nucleation sites. It develops the additional nucleation sites. When it develops the additional nucleation sites, some of the inert components, the molecules and the atoms, what are there, they start accelerate the process. They develop the assembly. That these nucleation sites assemble the molecules for a better hydration to accelerate the hydration process, and that produce additional CSH through the pozzolanic reaction. That already we have discussed just at the brief introduction of the pozzolanic reaction happens when there is some reactive material is there and we add some. See, we all understand in case of a cement, the prime components are like one is lime, calcium oxide, silica and alumina. So the calcium oxide, silica, when it adds with the water, that develops the CSS gel. But there are some ingredients like the calcium hydroxide, when it doesn't get excess amount of SiO2, it remains as a unutilized. That get attracts with the additional pozzolanic material, with the additional SiO2 content, it attracts along with the water, then it develops the additional CSS gel. The similar conventional process of pozzolanic behavior, it develops at the nano level. That's what it is. That additional CSS through the pozzolanic reaction with the CH2, it accelerates the hydration process. In that process, it develops a denser and more refined microstructure and reducing the porosity. That's the beauty of this. And if you look at the picture, right side of that, the developed microstructure. See, in that developed microstructure, there are 4 pictures are shown. In these 4 pictures, the first picture, let us imagine the compositions. In one, the compositions here is the conventional water cement ratio and micro and nano. See, some of here in the mixed case, the example figure what it is shown here, 3 kind of variations are made here. What are the 3 variations? 3 ingredients. One variation is the water cement ratio, another variation is the microsilica content, and another variation is the nanosilica content. As you understand, microsilica also improves the performance, and how the nanosilica improves, that we will see in the this demonstration, through the demonstration picture. See, here the water cement ratio is kept constant, that is 0.45 in the first figure. But 0,0, other two, there was no addition of microsilica, there was no addition of nanosilica, only the water cement ratio with 0.45. See, with the water cement of 0.45, how the microstructure is developed in the process of hydration. You are seeing that wide pores are there, large size pores are visible. We see. Then next, second slide. If you look at the second slide, in the second slide, you will see water cement ratio is 0.45. we have not added any microsilica, just we have added the nanosilica only. In second figure. In third figure, you see, we have added microsilica of 5% of weight of the cement and 0 nanosilica. Now you will compare the figure second and figure third, how dense with the 1% addition of nanosilica in comparison with the 5% of the microsilica. You will see the voids in 5% of microsilica is more in comparison to the 1% nanosilica. But now look at the fourth figure. If we have added microsilica and if we have added nanosilica, how dense the picture is. That's what the visual we can see. That is the game-changing activity of this nano form. So we can see the nanosilica modified, very compact and tightly packed CSS gel. We can observe. Now the question comes, if you add the nanosilica as like the conventional preparation of the cement, does it require any superplasticizer? Yes, it requires superplasticizer also. Why? See, if you don't add superplasticizer to the nanomaterials we are adding to there, in particular the nanosilica particles, tend to agglomerate due to high surface energy and reducing dispersion efficiency. See, these, as they are large specific surface area and small particles and through the high surface energy. When something with a high surface energy, as you all understand, it's highly reactive. When it is highly reactive, so when we add the nano particles into the concrete, what they happen, they assemble at one particular location. That is, you can see in the figure, left side figure, how the nano silica, they are clubbed at one location. So if they are clubbed at one location, we are unable to achieve our target. Our target is, let the help of our reaction, let the help in our hydration by utilizing the conventional material. In this process, what it is, in the process of agglomeration, they keep aside the conventional material and they themselves unite together, agglomerate, which is against our requirement, which is against our interest. So, but by adding superplasticizer, what you do, superplasticizer molecules coat nanosilica particles, creating electrostatic and steric repulsion. The steric repulsion, with the help of the steric repulsion, what they do, they positioning the atoms within a molecule through its electron cloud repel. So by doing that, it prevents the agglomeration and ensures uniform dispersion in the cement matrix. So that you see when they are agglomerated at one location, but by using the superplasticizer, how they can disperse. That in the right figure you can see. And this is, you can see in the pictorial form, when something without superplasticizer on left side of figure A and right side of figure B, you will see how well dispersed they are with the help of superplasticizer. With this well dispersed, what we can do, we can have a lot of benefit out of that because it helps to binding all the conventional ingredients what is there. So the right side figure A and B is collected from the TEM, the transmission electron microscope. That is why they say it captures the two-dimensional position of the molecules and atoms. From that, we can see that in left side figure, agglomerated particles visible without treatment, and in right side, well dispersed individual nanoparticles with the superplasticizer. That's what we have observed. Then, whenever you are adding the nanosilica, apart from the superplasticizer, and the quantity of nanosilica is also important role. Nanosilica fills the voids between cement particles, improve the packing density if it is in having some appropriate amount, required amount. But when it gets excess than the required amount, then too much nanosilica leads to small clusters that disrupt the matrix continuity. See, appropriate amount of nanosilica, it happens, is kind of able to manage to have the proper bridging between the conventional materials and keep them a proper filling of voids and improve the packing density. not only prevent the efficiency, also keep intact the proper from one material to other material, from one to other, effectively force transfer mechanism it does. But if with excess, some small clusters, small agglomerations, that cuts down the matrix behavior of the concrete. If more excess quantity is also there, then severe agglomeration creates weak zones and increasing porosity and reducing the performance. If something becomes a weakest zone in the concrete, because why it becomes weak? If they themselves stay together at one particular place, then they keep isolate the conventional ingredients. When they keep isolate the conventional ingredients, for the purpose what we have used the nanosilica, it lost its objective. Again, if we lost its objective, then we are unable to achieve our target. So appropriate amount of nanosilica is also an important role to reduce the porosity and to intact the performance of the concrete. That all whatever we discussed, this is the extensional part of that discussion only. Nanosilica particles have a strong tendency to stick together due to van der Waals force. Why they stick together? What I say discussed here, because of high energy, because of high surface forces. So when this high van der Waals forces, they stick together and reduce reactivity. So the agglomeration limits the available surface area for pozzolanic reaction with cement hydration products. That's what I will say. So when they not come in contact with the conventional particles, what it is there, then it reduces the reactivity. So there are challenges for this disbursement. What we understand here requires ultrasonic treatment and chemical dispersants or superstructure for uniform mixing. What we understood, we have seen in the example form also the material where we have not added the superplasticizer and the nanomaterials where you added the superplasticizer. If you added the superplasticizer, then you are getting the benefit of dispersion, proper uniform dispersion. So we can get out from the dispersion challenge. Also, it not only affects on the long run strength and immediate hydration process, it also has some negative effect on the workability also. Agglomerated particles increase the water demand and can negatively affect fresh concrete flow also. So not only that, agglomeration also have an anti-effect for the workability point of view also. That is what the new thing what we seen here. Now let us summary the nanosilica. Nanosilica reacts rapidly with the calcium hydroxide. If something is reacts with the calcium hydroxide, is like the conventional silica, what you understood the pozzolanic reaction, the nano-level pozzolanic reaction also happens, and that develops the additional CSS gel and enhances the strength. It fills the micropores and densifies the cement matrix, which reduces the permeability. That we have understood and demonstrated through the picture. Because of the proper hydration, you will have a strong interfacial transition zone, which refines the interface between the aggregate and paste. If the compact interface is there between aggregate and paste, which reduces the weak zones, effective force transfer mechanism happens. And this acts as a nucleation sites for CSH growth and accelerating the early age hydration. That I already understand what is the nucleation. It helps for develop a new phase for the hydration process. And it enhances durability. Why it enhances durability? Because of the reduction in the porosity and improves the resistance to all other external ingredient. Because of the atmospheric or extreme weather conditions, the chloride ingress, carbonation and sulfate, what are the many other things cannot be percolated, cannot be penetrated into the concrete because of its denseness. And that denseness comes up from the use of the nanoform of materials. This is another level of nano material, that is also graphene oxide. This graphene oxide, the way the nanosilica works, each individual nanomaterial has its individual significance, how they react with the CSS gel. So all don't perform the similar kind of reactions. They have develop different form of the reactions, and they develop different form of the adhesiveness. So here, the kind of things what you will see the different to that. See, if you look at what are the graphene oxide having? Graphene oxide sheets absorb ions like CO2 plus, OH, sulfate. They all are guiding the nucleation. The graphene oxide, whatever the kind of ions they are having, that is guiding the nucleation. So what you understand, the nucleation is a very good source of developing a new phase, and that new phase assists and helps and accelerates the hydration. See, in conventional process, if you look at, it develops the compound C2S, C3S in the process of hydration. That C2S, C3S helps to generate the CSH and the CH gels. And another one, the C3A plus gypsum, it develops the heterogeneous form, AFT form. And then AFT with the C3A, it develops the stable monosulfide phase. And these are the conventional practice. What are things happening? These phases happens with a game changer for the graphene oxide. So this, when it interacts with the graphene oxide, these hydration things, what are the reaction? I'm not going to deep up those reaction components. If you look at, it develops in the process of hydration reaction. When it assembles, it develops the flower-like crystals. So these flower-like crystals, the graphene oxide attracts and this organize the ions and directed assembly on a graphics oxide surface. And in that process, it develops the flower-like crystals. So these flower-like crystals, if you look at A, B, C, D, E, if you look at the flow, in the flow, you can see that Geo attracts and organizes the ions in picture 1. It organizes all the ions. Then in picture 2, directed assembly on Geo surface, it assembles. Then picture C, you see the growth into elongated flower-like crystals. And in picture D, E, F, if you look at the formation of mechanism in dense environment. Though finally, these whatever the arrangements they do themselves, they do arrange such a way that it develops a dense cluster. This dense cluster, what it develops, it has a huge impact to modify the morphology. When it modifies the morphology, it fills the open pores. When it fills the open pores, automatically it helps us the enhancing the strength and other behavioral patterns. Sorry, why I don't know, it's got a hang. Am I audible?
Yes, sir.
I don't know. Yeah. Sometime. Okay, it's good. See, so when the graphene oxide interact with the cement hydration products, CSH gel and calcium hydroxide, these hydration products, so it develops some functional groups. So these functional groups develops a kind of a other functionals, and these functionals helps for putting the proper bridge between the conventional ingredient to the nano geo graphene oxide. So that helps the formation of CaOC bridges, which anchors graphene oxide to hydration products. CaOC, these bridges, one is the calcium, oxygen, and carbon. These CaOC bridges, what it anchors with geo for the development of hydration products. These geo sheets integrate into CSH layered structures, which enhances the structural connectivity. That you need to understand. So in this process, Geo develops the CaOC bridge, and that CaOC bridge, when it develops, that integrates with the CSS layered structures, which enhances the structural connectivity. And these observations we can see in the pictures also here. So in A, the hydration products marked dispersed with the Geo presence. In picture B, Geo covering cement hydration particles as an uniform layer. In picture C, geo-coated clusters indicating nucleation on geo surface. In picture D, these graphene oxide substrates decorated with the hydration crystals. So that things is the procedural phenomena, what is happening in this nano geo. So geo acts as a reactive scaffold, which is chemically bonding between hydration products. So that helps for densification of the cement matrix and for its growth also. So how do you prepare this graphene oxide? And how do you, it helps us? So this is also, and how do you get the benefit out of this graphene oxide? That if you can look at here. Graphene oxide improves chloride and sulfate resistance and lowers permeability for a dense microstructure. So when you add the graphene oxide, it improves the sulfate resistance and chloride ion resistance. And this sulfate resistance chloride resistance is very good source of restricting your reinforcement corrosion. And similarly, it helps accelerating the hydration process. As like your nanosilica also increases cement hydration rate due to high surface energy and hydrophilicity. So because of hydrophilicity, it quickly attracts the water to it. When it quickly attracts to it, prior to other ingredient attracts the water, in that process, the hydration, it accelerates the hydration process, increase the hydration process. If you look at the plot here, in time versus reaction rate, the graphene oxide with less time, more reaction. In control state, it takes more time to get that similar level of reaction rate. So that's why that benefit is also there in from of graphene oxide we are gaining. Not only that, it helps to boost the both strength and both mechanical property, both compression strength and tensile strength also of the concrete. But these are the essential criteria, these are the essential parameters of the graphene oxide, which helps us to use. That is, it's because of aspect ratio, high aspect ratio, and hydrophilic. It develops high mechanical strength and high surface energy. Is like that, nanosilica. So, in summary, geosheets act as additional nucleation centers, which accelerates the CSS gel formation. Interfacial bonding also good because of oxygen functional group on graphene oxide form strong bonds with cement hydration products. And because of that, it bridges the micro crack. Graphene oxide sheets bridge micro cracks, enhancing tensile and flexural strength. And it modifies the hydration. Geo can refine pore structure, leading to reduced permeability and improved durability. So with the hydration, is like the previous nano silica also, it refined the pore structure and reduce the permeability and improve the durability. Now this is another form of nanomaterial, that is the CNT, carbon nanotubes. See, CSS gel with nanoscale porosity provides sites for CNT incorporation. In conventional hydration process, it develops the CSH gel. Inside that, there are some pores, gel pores are there, capillary pores are there. So these gel pores and capillary pores, they remain in the nanoscale. And those nanoscale porosity gives the site for this incorporation of these nanomaterials. So this CNT is physically embedded into the CSS network, filling the voids and bridging the micro cracks. CNT surface attracts and binds Ca+ ions, enabling further CSH growth. As you say, every nanomaterial is good for developing the nucleation sites. here also same thing happens. The nucleation of CSH on CNT surfaces strengthens the interferential bonding. And carbon nanotubes become a part of the cement hydrate network, which enhances the load transfer and durability. So the load transfer and durability is the very important parameter, kind of a nano substance, nano concrete, because anything, if there is the proper bridging is not there among the material what we are using, then the loads what is coming to that structure, what is coming to that product, it cannot effectively transfer the load. So effective transfer of load depends upon how organized all the atoms and the molecules and what are the materials are there inside the concrete. So that is important. So that's why the microstructural integration, microstructural rearrangement, microstructural development of a concrete is a very important phenomena for its macro behavior. So this process shows how the carbon nanotubes helps in assisting its growth inside the porosity, how assisting its reactivity and its hydration, how it enhances, all those things are discussed. So CNT significantly reduce total pore volume, that we understand, and shift the pore size distribution towards the smaller diameter. So when the concrete is improved by its pore networking, then automatically you will see that it is refining the porosity. So microstructural densification, 3D models reveal denser packing and hydration products with the CNTs. If you look at the three-dimensional model, how densify your substances, that you can see pictorially. If you go look at the MIP, some of the pictures collected from the MIP, that the mercury intrusion porosimeter data shows reduced critical pore diameter from 7 to 8 nanometer in plain CSH to less than 5 nanometer with CNT addition. If you go for the conventional cement, then the kind of pore what is observed 7 to 8 nanometer, that pore size with the addition of CNT reduced down to less than 5 nanometer. So nanoscale strain maps indicate more uniform stress distribution than non-CNT composites. See, if you look at the picture here, the pore diameter versus the volume, what it is shown there. So it is seen that how distributed it is, how the strain distribution is shown. It is not strain distribution from the volume, how it is there in the less porosity kind of things, how compact it is, that is being quantified in this figure, how compact the substance is. Then CNT presence minimizes localized high strain zones, delaying microcrack initiation and propagation. So that you can see in the failure mode graph, the change in fracture process and failure mode. If you look at, see, the different colors gives the different stress level conditions. Some of the particular concentrated stress you can see if there are some crack lines are there, some failure fracture process lines are there. And when it well dispersed, well compacted, then you see all are not concentrated one plus how they are segregated. The colors are segregated. That means, see, inside the concrete, if void is there, it is acceptable. But the void should not be connected. If the void is connected, then it enhances the permeability nature of the concrete. So void is there, but voids are not connected, then it will not harm you. That's what you have seen here. When the voids get connect, with the effect of load, with the effect of stress and strain, those develops the microcracks. Those microcracks becomes a bridge between one void to another void. So those microcracks, if blocked, they are protected, then we can not connect all the voids. What are the void means I am telling it in terms of nano level. I am telling in terms of micro level. those micro the mesopores, those micropores should not be connected one form to another form. If they are connected, you can enhance the failure process. I mean, accelerate the fracture process. That's what we have observed here. So this is the way the carbon nanotube is used. And another important benefit of the carbon nanotube is that what you can see here, that is that it changes the electrical resistance under mechanical strain. When something is changing the electrical resistance on the mechanical straining, it enabling self-sensing concrete. So when you go for use of the nano things in due course of slides, we will discuss that. What is the, we are not here so far, we are discussing about the strength and microstructure behavior, durability, all those aspects we are discussing. But it is another beautiful aspect of this nano level concrete is kind of a self-healing, self-sensing, self-cleaning. So these are the important items also we can get benefit out of this nano level concrete. So the nanomaterials, what we are using, so what it helps us in the process of mechanical phenomena. Mechanical phenomena, when there is the concrete will get the load, it will develop the stress and strain. Alternatively, that stress and strain will convert to the electrical phenomena. It will convert the mechanical energy to the electrical energy. When it converts the mechanical energy to the electrical energy, it will perform as an electrical insulator or as an electrical conductivity or as an electrical transmission kind of a resistance. Those things can be measured by using this nano substance like CNT also. If we do that, then we can monitor, we can sense the property of the concrete. So the mechanical thing converted to the electrical property. So electrical property can be measured. So from that measurement, we can sense the state of the concrete and condition of the concrete. That's why it is a very good material and it's a very good item to understand in due long run. If there is, because of the mechanical process, if there is any kind of cracks, any kind of vibration impact is there, if those cracks are going to propagate or they are propagated, and those things can be monitored using the structural health techniques. So the structural health monitoring in real time is also important item required these days, and these materials is a useful tool for those structural health monitoring also assessment. So it bridges the cracks and helps in pull-out resistance. As you all understand, like other nanomaterials also, CNT spans micro cracks and resist pull-out, improves the fracture toughness. As like others also, here also, this also improves the leaf clearation and hydration enhancement, accelerates the hydration and develops the additional CSH growth, and effective load transfer because of high stiffness and aspect ratio, enable effective stress transfer between cement matrix and the CNTs, and it fills the nanopores and reduces the pore connectivity, enhancing the durability, as you understand. Now, another important concrete we can made out of this nano TiO2. It is an important item to understand. See, so far what I discussed, we are very good. It is very good to use the nano substances to improve the strength, to improve the physical structure of the concrete, for gaining its durability, all those aspects. But here we are discussing something interesting of self-cleaning. How the concrete can clean self, that we will see. See, if we are using TiO2 in concrete, it acts as a photocatalyst under ultraviolet light. In atmosphere, we are having some pollutants like nitrous oxide, nitrous dioxide, NO2, and NO2 are both nitrogen oxides. And how this nitrogen oxides forms? These are pollutants which are sourced from high temperature fuel combinations, combustion, particularly from vehicles and industries. If some of the structures are concrete are nearby industry, and some of the now this all the big cities with large the pollution comes out of the vehicle running in the big cities, and they produce large amount of nitrogen oxides. These pollutants, what they come in contact with the concrete, it keeps the pollutant layers onto the concrete. But with the help of this TiO2, what it does, when these nitrogen oxides interact with the ultraviolet radiation generates reactive oxygens, then it oxidized into a harmless nitrates, NO3. So see, if you look at the picture, concrete with the TiO2, then concrete with the TiO2, when it attracts with the NO and NO2, the pollutants doesn't remain in the concrete as a layer. What it does, when it comes in contact with the ultraviolet radiation, it develops another new product, that is NO3. And that new product, when it comes in new product, it is having a property of self-killing and air purifying effect. It doesn't stay there. It goes out along with the water. It goes out, moves out along with the air from the atmospheric water on atmospheric air. So it doesn't come, when it doesn't remain as a layer in onto the concrete, it removes, cleans out from the concrete. And that is a very beautiful phenomena, what is happening. Why it is so happening? If you look at the bottom of that, see this TiO2, what is there inside the concrete, when it comes in contact with the light and these nitrogen oxides, it develops the NO3 if it will have some active oxygen. This active oxygen comes out from in contact with the ultraviolet lights, ultraviolet radiations. The ultraviolet radiations and the sunlight, they come together, when they come in contact with this TiO2, it develops the active oxygen. That active oxygen, when it comes in contact with the nitrogen oxide, that develops the NO3. That NO3 automatically comes out from the surface of the concrete. But when this, sometimes this TiO2 also remains as a dormant from reactivated form, then it is dormant from reactivated form when it is coming in contact with the calcium carbonate. So that whitish calcium carbonate doesn't allow the contact of ultraviolet with the TiO2. When doesn't allow the ultraviolet with the contact with the TiO2, so the NO layers, what is there inside, they are unable to clean out. That's why when it comes in contact with the ultraviolet radiation and sunlight only, then it works as a self-cleaning activity. Or else the CO2 deposition limits the surface activity. But to have a surface activity, the surface has to be exposure of TiO2 with the ultraviolet and light. So that's why these nitrate ions, the nitrogen oxides, when converted into nitrate ions, NO3, it washed away by rainwater or some aerosols. That's what the self-cleaning mechanism happening with the use of the TiO2 inside the concrete. So this photocatalytic action promotes degradation of pollutants on concrete surfaces. See, now not only concrete surfaces only, see nowadays you will see many facades or many glass like claddings, many decorative claddings has come out which are used in the high-rise buildings and high-rise structures. So those high-rise structures, those high-rise claddings, also if you use this nano TiO2 inside to that, then also it helps as a self-cleaning material. Because it is very, very difficult to maintain, to keep the clean of the very high-rise locations. So this TiO2 is a very good phenomena for the self-cleaning of those structural those non-structural components and those some aesthetic components what are in use. So the microstructure refinement fills nanopores and improves the density and reducing the permeability. It enhances the hydration, as like others also. It accelerates the early hydration reactions. And most important item, the self-cleaning effect. This nano TiO2 maintains surface whiteness and reduces maintenance needs. If something is automatically clean, then it helps the less maintenance. Then another component, which is called nano alumina, is like others. It is also acts as additional nucleation points, boosting the CSS gel formation and enhances the strength, both compression and flexural, by densifying the microstructure. Is like others also early hydration acceleration, promotes rapid setting due to high surface reactivity, improves wear resistance in pavements and industrial flooring. And how these things are happening? Because it uses the extra calcium hydroxide, what is there as a pozzoning behavior, improve compressive strength, and enhance the RCP ability. That RCP is nothing but your chloride penetrability inside the, it reduces penetrability of the chlorides inside the concrete, and it refine the pore structure and increase the dye density. As like others, this is similar common phenomenon also observed in the case of nano alumina also. Similarly, the nano Fe2O3 is like others, it is also having pozzoning interaction. As like others, it is also resistance to chloride ingression, sulfite attack. But additional thing it is there here is a thermal stability. It enhances the fire resistance due to high thermal stability. So in comparison to others, one added benefit of this nano Fe2O3 is that it is having a thermal stability. Because of the thermal stability, it enhances the fire resistance inside the concrete. Some aesthetic point of view also, it imparts some reddish brown tint for aesthetic and functional purposes wherever it requires. As like we have heard the dispersion problems there in nanomaterials. Why the dispersion problem? We have already discussed this issue. Because of high surface energy and high van der Waals force cause the particles to clump together and reducing the effective surface area. And pore wetting, because of hydrophobic nature of some nanomaterials, limits uniform mixing in aqueous cement pores. See, hydrophobic nature is also very negative parameter of this nanomaterial. There are some nanomaterials which are having hydrophilic in nature, and some nanomaterials which are hydrophobic nature, and that needs some special care for its proper mixing. And all you understand, because of non-homogeneous distribution, clustering, agglomeration effect, so non-uniform spread leads to weak zones and inconsistent mechanical performance. All we have understood. The challenge is there, conventional cement mixes methods may not generate enough shear to break agglomerates. So the way we practice the conventional mix, that is not good enough for proper breaking of agglomerate particles. So it requires special care by from a superplasticizer or the other mechanical means. So large agglomerates can act as inert inclusions, impeding hydration and microstructural refinement. So that should be taken special care and utmost care. So how can we improve the dispersion? How can you reduce the agglomeration? Those things are taken care by using proper mixing during the physical solution process. And also we use some mechanical high shear mixing or wet mixing method to achieve homogeneous distribution. Then we are using some dispersion or superplasticizer to improve the compatibility with the cement matrix during the chemical solutions. So one way mechanically we can improve, another way by adding the superplasticizer we can improve. So both way we have to take care, both physically and chemically. So in chemically, we have to add the superstructure, and physically, we have to do some kind of mechanical means of mixing. There are some classifications of nanomaterials. So we are not going to discuss in detail of all the classifications. In particular, what are of we interest, what are the used for in particular to the concrete, like some of the this inorganic metal-based, metal oxides, lipid-based, ceramic, semiconductor, they are in use, and there are some carbon-based are in use in the concrete. Inorganic and carbon-based are there in the concrete. And how do they look like? How the nanofibers look like based on the dimension. See, very small zero, it depends on zero dimension. If the nano particle is significant in only one particular dimension, that is the one dimension. If it is significant in the two dimension, it is two dimension. It is significant in three dimensions, though it is small in size in terms of nanometer. But looking at the aspect, they are classified. 0 dimension, 1 dimension, 2 dimension, 3 dimension. Also, some of they are based on their use, in which kind of pores they are in use. Accordingly, they are micropores, mesoporous, and macroporous. And based on the origin, if it is prepared artificially, then its base is artificial origin. If naturally it is available, then its base is natural origin. Like this, they are classified. And based on the toxicity, how much precaution you should take whenever you are using it, accordingly also they are classified. That is how the physical look, the nanomaterials, based on their dimensionality, based on their morphology, based on their composition, and based on their agglomeration state. How they look like. That is being shown here physically, pictorially. So as you look at the fundamentals, the basic things of the nano behavior, it is not for a single use. We are using the nano materials into the concrete, not for enhancing strength, not for enhancing durability only. You have seen that many places for self-cleaning, for self-healing, for temperature resistance, and also structural health monitoring. And wherever we require some multi kind of functionality, it is very useful materials. So these things are being researched and presented in different literatures. They are summarized here. In recent literatures are gathered and collected and summarized here, and they are presented. So in 2021, that improves the fractural resistance, durability, and mechanical strength. And another is smart sensing capability of the by using carbon-based nanomaterials, self-sensing, what we discussed from the past in the last discussion in the last slides. And another is self-healing capabilities, what that also we have discussed. And thermal insulations, that also we have discussed. Enhanced durability and self-cleaning. So all these, so it is not only particular direction only. So multi-dimensional use and multi-functional use, multi kind of varieties applications. That is being summarized here. So again, what was discussed there, they are again summarized. The nanosilica, it is having some filler effect and pozzolanic reaction. And sustainability impact, it is there. Because of that, you can use less amount of cement to gain high strength concrete. Similarly, carbon nanotubes, it is a crack bridging, electrical sensing, longer life, and smart monitoring. Nano TiO2, photocatalytic self-cleaning surfaces, what you see, which helps in the lower maintenance. Similarly, graphene oxide, enhanced iteration, improvability, and it also enhances the durability. Also, it is not being mentioned, it is also good for the condition assessment also. Structural health monitoring also it is used. Self-sensing things are there. And nano Al2O3 also improved abrasion resistance in infrastructure longevity. See, if you look at the concrete, there are different properties of the concrete is governing with. One is compressive strength, tensile strength, flexural strength, shear strength, and other durability parameters. and other agent required parameters like self-cleaning, self-sensing, purification, and the extreme weather conditions, and some phase property improved conditions. All those properties, phase property, hardened property, and self-sensing property, all other, they are all the listed out atoms, and they listed out nanomaterials. If you look at how they are correlated, and one is negative effect, one is neutral or inclusive effect, and the positive effect. So most of the time, if you will see that mechanical point of view and durability point of view, you will see that all of they are the positive effect, but only in the sense of workability and cost, you will see it is a negative effect. Because as we learn from the understanding of the fundamentals, so because of the hydrophilic effect of that, so it attracts the water, and when it attracts the water, it has a great influence on the workability point of view. So that is a negative part of that nano use. And also whenever you are using the nano level thing, so based on, because of its manufacturing process, it is higher in cost. But though initial investment is high, long run benefit is there, that you can see from the life cycle assessment, from the economics calculation, you can get it, how benefit it is. But initial investment, true, yes, it is a costly item. Initially it's a negative effect. And there are some neutral and inconclusive things are there. Some particular materials is good for that particular case, and others are not good for that particular case. That's why. And some of the observations also being not made out of that study. That's why some of things cannot be, some clarifications has not come out yet. So these are being focused and summarized here. So the first part of my discussion was towards the nanomaterials, how it is performing related to its behavior. Now, if we use why it leads to the sustainability, this part we will discuss here now. So why nanomaterials lead to the sustainability? If you look at the question to that answer, your answer comes out here. We all know structure weakens over time. When the structure weakens over time, if we have to enhance the capability of the structure for long run and improve the life of the structure, then definitely nanotechnology is an important tool. Nanomaterials, addition of nanomaterials is a new direction, a new game changer. Because of its higher strength, we can minimize the requirement of the material. If you minimize the requirement of material, then automatically we will enable with the lighter structures. If you go with the lighter structures, automatically it reduces the load on the foundation also, or direct or indirect, it will lead to a overall a life cycle economical design. And also by using selected materials, we can get a little less maintenance cost also. So that's why it leads to a sustainability requirement for the nanotechnology. All other things already we have discussed. Only the items what I would like to add here. The nanopolymer modified bitumen improves the rotting and fatigue resistance. So in roadway, we are seeing the rotting is a very common phenomena, and fatigue failure is a very common phenomena in roadway. That is what you all understand. The rotting is nothing but a permanent deformation of an asphalt pavement because of the movement of the wheel during high temperature and repeated traffic loads. And these things get protected by high modulus asphalt mixtures. So that high modulus asphalt mixtures we can create, we can improve upon by using nanopolymer modified additives. So that is what was not discussed in last. That's why I added here to this discussion. So it is a huge engineering benefits that already we have seen. With that, we could able to increase the strength by 15 to 25%, and we can able to reduce the permeability by about 40%. So by doing so, It can avoid the catastrophic failures and minimize the maintenance, both longer lasting roads and reduced maintenance, and also enhance the service life. Because of self-cleaning, it improves the aesthetics also. So as you see, sustainability is having 3 pillars. One comes out from the environmental sustainability, another comes out from the economic sustainability, and another comes from the social sustainability. See, the economic sustainability means ensuring cost effectiveness and long-term economic benefits. See, initial cost may be more, but if you could able to long-term economic benefit, then we can go for a viable nanotechnology modeling or nanotechnology application to our construction sites. Similarly, environmental sustainability, because it is a huge ecological impact, lowering emissions and conserving resources. See, whenever we are using the ingredients, whatever ingredients we are using in the concrete, if we could go for longer life structures, automatically it will be a great impact on the ecology. It is a great impact on the emission and conserving the resources. Social sustainability, if we are improving the performance of the structure, automatically it is promoting the safety, health, and social well-being. So all the 3 kind of sustainability we could able to achieve if properly we are using the nanomaterials into your construction. But still there are challenges that can be minimized using this nano. Those things are taken care in environmental sustainability, because in environmental, the cement production is a high carbon footprint, that we understand. That can be minimized. If you are using less quantity of cement, then automatically we are minimizing the high carbon footprint of the cement. So if we are doing that, then also we are able to contribute significantly to greenhouse gas emissions also. So when it comes to durability related premature failures, automatically those things also being discussed in the kind of environmental and economical factors. And resource depletion, this is also discussed there in the kind of environmental sustainability discussion. So all the things can be taken care in nanotechnology to reduce the waste, to extend the lifespan, to improve the efficiency. So whenever we are meaning a sustainability in civil engineering, we are meaning optimizing of use of the materials. So appropriate proportion of concrete constituents, if we are doing, then with appropriate selection, with the optimum selection of the materials, we can reduce the wastage in use. So using nano additives for performance improvement with smaller quantities, then as we discussed, we can reduce the cement content, we can reduce the CO2 emissions, and we can improve the performance. Similarly, recycle and waste management. Reusing of the construction and demolition waste as a recycle aggregate, incorporating industrial byproducts, and minimizing disposal impact and closing the material loop. These are the helping tools for recycling and waste management. Similarly, how can you do the sustainability? By using innovations in materials. Like now, I was seeing there are a couple of lectures related to geopolymer concrete. There, those experts also will explain you in detail what is the benefit of geopolymer concrete, what way it contributes to the sustainability also, what way it contributes the reduction of carbon emission, reduction of carbon footprint. And also limestone calcinated clay cement is a recent development also. This is also can reduce your carbon footprint, or bio-based admixture also reduce your carbon footprint. These innovative materials also lead towards a sustainability. Introducing 3D printing for concrete structures also can reduce the waste. Designing longer lasting structure with better durability, it is our objective and motto. And applying life cycle assessment to ensure minimum maintenance and extended service life. So any structure to reduce the carbon footprint and to go for optimum use of the material and to go for a sustainability, both environmental sustainability and on social sustainability, all those things, life cycle assessment is an important tool to understand for the extended service life. And by all together, if you optimize the structure, then you can get a lighter, safe, and longer life structures. Now the thing is, to hear this, the AI, artificial intelligence, and machine learning based optimization tool is an effective platform for combining all these effects into one place. Both LC analysis, material optimization, and waste optimization, and how to incorporate the property into account, individual material property into account, get a macro prediction. All these things all together we can do by utilizing our large databases. This machine learning tool is an important optimization tool to come forward for its use. So as you know, life cycle assessment is a systematic tool for evaluating the environmental impact, what I was discussing, from the raw material extraction to its end of disposal or to recycle use. It can extend a service life, lower replacement frequency over 50 to 100 years, and you can save the maintenance up to 30 to 50% reduction in repair cycles, and pollutant mitigation, air quality improvement, you can do using nano TiO2. Longer life means fewer demolitions. Environmental benefits outweigh higher initial manufacturing emissions of nano materials that I was already discussed. See, if you use this nano silica in comparison to other conventional filling material, if it's cost 10 to 20 per kg, then it happens to 8 times higher to that, 80 to 150 kg per. Similarly, CNT and graphene can be also 10 to 100 times costlier per unit weight. As we know, because of agglomeration effect, we need a special dispersion technique, both at chemical level and physical level. And additional quality control steps are required. And it also requires the personal protective equipments for nanoparticle handling and skilled labor for mixing and placement. So these are the additive costs. But what the benefit we are getting? Structure lasts 2 to 3 times longer, lower replacement frequency, reduce the repair due to improved durability, impermeability, and crack resistance. Reduce material use also use, because as it has a high strength, reduce the amount of steel and cement. Because of that, we can lower the embodied carbon energy and raw material cost also. Energy savings, less frequent production and transport of replacement materials. Eligible for carbon credits in green building certifications. What are the challenges in the adoption? All you have gone through the dispersion challenges because of agglomeration effect and mixed design compatibility because of what proper water cement adjustment and admixture things. Lab results usually don't match with the field performance. These are the technical challenges. And economic barriers, high initial cost, lack of local supply chains. These are the limitations. Many of nanomaterials are imported. And health and safety concerns are there. Inhalation risks, fine particles can be hazardous during handling. And proper trained workers should be there in the site to use it. and unavailability of the standardizations. There is no unified code for use of these nano additives. As the adaptive unified codes are not available. So definitely, whenever it will use the regulatory uncertainty, approval process will be slow to adapt it. These are the future trends, what already we have understood. These benefits, self-sensing, self-healing, energy harvesting, all the items we have discussed in due course of discussion of these nanomaterials. This is also continuation of that, what we have discussed. Continuation of that, what we have discussed. But one item I'd like to emphasize here, the machine learning models to optimize nanomaterial dosage, cost, and performance is now the advancing tool which are in process of research. All the data, what are they gathered, and they have to be utilized for properly for machine learning development of machine learning models, which will help us, which will make our life easy, how to use the nanomaterial effectively. As it is usually a smart sensing technique, so the embedded nanosensors for Internet of the IoT-based monitoring of temperature, moisture, and training real time we can measure. So IoT, all you understand, Internet of Things, many items are now connected to the Internet activity. So by sitting at your place, by using the sensors at your site, we can monitor the condition of the concrete. That's the beauty of that. So when you, by sitting at your place, by sitting at your office, you could able to monitor the status of the cast of the concrete, then how better control, quality control you can imagine. So these are the future trends which is ongoing. Here I am giving glimpse to the how can you utilize the multi-scale machine learning models to study the behavior of nanocomposites. See, as you see, we are looking at the property at the nano level, and we are expecting the we are simulating the things at the nano level, and we are expecting the property at the macro level. And also we have seen that in form of the scale, there is a wide gap. See, something is 10 to the power minus 9 to the 1. So how big difference the scale is? So all the things to correlate them and to predict the property from the level of 10 to the power minus 9 simulation to the meter scale, we need a multi-scale approach. And this multi-scale approach, if you go for mathematically, then it gives a huge kind of computational effort. In it can have computational time and computational setup. It can be minimized by using machine learning. How it is? See, look at the nanoscale simulations, what we are doing. We are doing the machine learning analysis. Then that machine learning analysis data in form of transfer learning, we are giving to the another scale data, micro scale. So the micro scale, it's doing its own analysis and develop the machine learning model. Then it drags the transfer learning data from the nano level. Then by combining machine learning data up at the micro level and transfer learning data of nano level, it develops a new model. Again, that new model, it converts to transfer learning to the another mesoscale data. So mesoscale data develops the machine learning model, and it gets the transfer learning data, what was gathered at nano level and micro level information, and that data it takes and it develops another new model. That new model it stores and transfers to the macro property. This macro property finally we are observing, and so all the real-time parameters of nano transfer to the micro, and micro transfers to the meso transfer to the macro. And all these things are happening in form of transfer learning and machine learning models. So for this, we require a huge level of database, and which are in process of collection. So when we will have a huge process of data, it will be a useful tool, useful application of by minimizing the large computational tool and predicting the nanoscale data to a macroscale data. That's what it is. So here is the conclusion, whatever you discussed so far. Nanomaterials as a performance enhancers. The incorporation of nanomaterials significantly improves the mechanical, durability, and functional properties of cementitious systems through pozzolanic activity, nucleation effects, and microstructural densification. Each nanomaterial interacts differently with cement hydration products, influencing CSH formation, pore structure refinement, and secondary hydration reactions, thereby tailoring specific performance outcomes. Proper dispersion of nanomaterials is essential to fully exploit their surface reactivity and avoid agglomeration, which can otherwise reduce the expected benefits in strength and durability. Certain nanomaterials impart multifunctional properties such as photocatalysis, antimicrobial action, or piezoresistivity, opening opportunities for smart and self-sensing concrete applications. Using nanomaterials derived from industrial and agricultural waste supports low carbon, resource efficient construction, aligning with green building goals. The integration of multi-scale machine learning models with experimental data enables accurate prediction of nanocomposite behavior across nano, micro, and macro scales, facilitating optimized mix design and accelerated material development. Thank you. These are all the references what we have used to prepare these contents, and thank you all for your patient hearing. I think I could able to complete the task in time.
Yeah, exactly, sir. Exactly. Now 7:59. Sir, and one more thing, sir. Our entire participant 97 in the beginning and 97 at the ending also. All are the available, sir. Really very useful material you shared, sir. Thank you very much.
Thank you. Thank you. Thank you.
Shibani, you can or Archana madam.
Good evening, everyone. It is my privilege to introduce Dr. V.S. Barma, a distinguished academic and industry leader with over 30 years of experience, including 24 years in leadership roles. Dr. Barma has served as principal in several engineering colleges, leading them to key milestones such as NAC accreditation and establishing over 250 UG and PG laboratories. He pioneered India's first MTech program in design for manufacturing in 2004 with a PhD from NIT Warangal and senior roles in industry including as general manager at Bajaj Ecotech and EcoBoard Industries. He brings a rare blend of academic excellence and industrial expertise. He has earned 14 plus NPTEL certifications in cutting edge areas like AI, IoT, Industry 4.0 and leadership with top including of Gold, Elite and Discipline Star. We are honored to have him with us today to share his insight on academic leadership, innovation and integration of industry with education. Finally, I request Dr. B.S. Verma sir, please take over and begin the second session of this FDP. Thank you all once again for your presence and participations.
Welcome, sir, Dr. B. Srinivas Verma, sir.
Sir, may I intervene, sir?
You can share it.
Sir, no, sir. Sir, this is Professor Spatro. Sorry, before the next speaker took over if anybody is any question, 1 or 2 questions, we can take.
Yeah, sir. Sorry, sir. Actually,
we cannot give scope to the others audience to ask the questions.
Right, sir. Actually,
if your
we
time
also
permits,
busy.
it's okay, or else it's fine. It's up to you.
We can ask, sir. We can ask. The audience can ask questions. The faculty who are attending this program, any questions in the first session, sir is ready to answer queries. They can unmute their mic and any questions, or they can give the chat.
Yes, you can. Or they can post it later on also. I can respond to their queries because it's time to start for the next lecture.
Yes, sir.
No problem. Thank you.
Okay, sir. Sir, any questions are there? We will pass on to you, sir.
Yes, sure. Welcome. Thank you.
Good evening.
You can unshare, Synesis. You can unshare the screen, and sir will share the screen.
Good evening to everyone. Hope I am audible.
Audible, sir.
Yes, sir.
Yes, sir. Audible, sir.
One more test. I have to share my
Screen is coming, sir.
One second.
Yes, sir.
Yes, sir.
Yes, sir.
One second. One more second.
Sir, previously it came, sir.
No. It will come. It is taking some time. Yes. It will take a minute. Now it's okay, sir?
Now coming, sir. Excellent.
Yes, sir.
You can proceed, sir.
Yes. This is one of the finest topics that you have chosen. I should congratulate the coordinator, Archana Anand Madam, and the principal and the director of MITS, and the vice chairman, Biswajit Panda. And this is the apt for this particular moment for India. And basically, the future of eco-friendly binders motivates me because India's first eco-friendly particle board, I was a part of that, wood-free particle board, and it is somewhat related to that, and it is on the material side. Yes. The topic is geopolymers and alkali activated materials. The future of eco-friendly binders incorporating TRIS, theory of inventive problem solving, and performance indices and SB charts. I am Dr. Srinivas Verma. I am presently Director of Accreditation and Academics, Apex Education and Technical Services at Hyderabad. This is the future of the geopolymers in the next 10 to 15 years. The future of eco-friendly binders will be everywhere, from the highways to the airports to the buildings, everywhere. So, as we know, the cement is the main construction material, and the cement contributes overall 5 to 8% of global CO2 emissions. So this is a very, very, very high, as you see that, because the high energy demand due to calcination of the limestone and other materials happens at 1450 degrees centigrade. That's why there is an urgent need for sustainable binders. Here, why the geopolymers and what are geopolymers and what are AAMs? AAMs are nothing but alkali activated material, and these geopolymers are a blend of fly ash, slag from the steel plants, metakaolin. Metakaolin is basically from the clay, kaolin clay. We have seen bentonite and kaolin clays, and a transformed kaolin clay is basically metakaolin. And then, because why we go for this particular geopolymers? Because of reduced carbon footprint and circular economy support. What is the circular economy support? Because fly ash at one time is a waste. Now it is more in demand. More than 90% of fly ash is utilized everywhere in India. If you see the carbon footprint and its comparison with the geopolymer and geopolymer with the green activator, you could see that OPC cement, Portland cement, will have around the carbon will be released, means in the form of carbon dioxide, is released 800 kg of carbon dioxide per ton. And if you see the geopolymer, it is around 400 kgs. And geopolymer with green activator on the right, that is green activator is with a hydroxide, also known as hydrated lime alkali hydroxides, blast surface furnace slag and carbonates, it would give much less, around 250. So this is the drive. Basically, we want to reduce the carbon footprint from 800 kgs per ton to about 300 to 400. This will be possible. Yes, this is made possible. The scope of my presentation will be material science foundations and sustainability and cost, applications and case studies, TRIZ-based inventive problem solving, ASB charts and performance indices, and trends and limitations and way forward. What is the chemistry and the reaction mechanisms? Chemistry, here it is. There are two: geopolymerization, aluminosilicate networks, and hydration. Basically, we're seeing the hydration with the cement, what we call as a CAS. But what we say with this geopolymer, cash gels, CASH gels, and hybrid binders, combined both the benefits of these two, geopolymerization and hydration. What is geopolymerization? Geopolymerization is a chemical process where aluminosilicate-rich solids react with alkali solutions. What is the alkali solution where we use? What we use here is sodium hydroxide and sodium silicate. You know, sodium hydroxide, Na to NaOH twice, and because this is durable and amorphous and inorganic polymeric network, which forms a bond of SiOAl, means silicon, oxygen, and aluminum bonds. This is basically geopolymerization. If you see the what is the chemistry of this? If you see the first one, step one, where this geopolymer material is added with alkali material, and this is dissolved and gel will be formed. It is polymerized and it will grow. And the green one shows a silicon, and then Al is a violet in color, red color is oxygen. If you could see that it is totally in a well net. It's a well net. It's not any broken chain over here. This advanced cement chemistry key concept related to geopolymerization are basically it is a formation of strong, durable 3D aluminosilicate networks by alkaline activation. Here it is alkaline activation, and then eco-friendly alternative to traditional cement. The question will come and answer also will come in few minutes. Can the cement can be replaced? Yes. Whether it is being replaced? Yes. What is the next few years? Next 20 years, 30 years, 40 years? Yes. Whether it is sustainable? Yes. All the answers are yes. Whether it is economical? Yes. Whether it is durable? Yes. And the hydration. Normally we see the hydration in the cement. Water reacts with calcium, alumina, silica, and forming calcium aluminate silicate hydrate gels. And of course, the hydration here we are referring it into geopolymer things where CASH will come, calcium alumina silica is coming, and whereas in the case of cement only it is only CAS. And this particular slag system, what it is called as a slag system, because we are using the slag from the steel plants. Every cement is nowadays is being produced with the slags, and we can also combine geopolymerization with hydration. That is what we call as hybrid binders. Here, if you can see what is geopolymerization with a simple sketch, you can understand. And this is a metal, and SiO2 and Al2O3 is you can see, and ultimately it is coming as NASH. What is NASH? Yes, we will explain. And what is hydration here? CaO and SiO2, and this becomes CaSH. Okay, CaSH. And sorry, initially I said CaS. No, it is not CAS, it is CaSH. And hybrid binders is basically CaSH. The hybrid binders are also being popular, and this hydration is specific to the cement, what we are using today. If you see the geopolymerization, alkali cation, either sodium or potassium, is a part of the aluminosilicate precursors, and when they are dissolved, and polykondensation will occur, and it will come as NaSH gel. NaSH means basically sodium aluminosilicate hydrate. And hydration, the Portland cement, what we see is the calcium oxide and silicon dioxide, and with H2O, it becomes hydration. This is called as calcium silicate hydrate. Then hybrid binders are alkali and aluminum silicate, and both you do the geopolymerization and hydration, you will get CaSH, that is calcium, or either calcium or sodium aluminosilicate hydrate. These are the three main reactions, either geopolymerization or hydration or hybrid binders. This CASH, that is CSH and CaSH and NaSH. These are the three preliminary things what we could see in this geopolymerization versus OPC cement. Here, if you see the image of the geopolymer, you see beautifully things are there. It is well woven web. H2O is basically in a yellow color. Sodium is in a blue color. Silicon, SiO4 silicate, basically it is in the brown color, and alumina is basically in the blue color. So it is a very, very clear web, not broken chain. But if you see on the right side, that is on the OPC, that is Portland cement, where only CSH is there, you could see SiO chain, you see calcium oxide sheet and SiO chain, and then intermediate layer, interlayer, calcium and hydrogen, water rather, H2O, then SiO chain, and then again like this. You could see means this is at a 1 nanometer level. You can see that nanometer. So basically, see the right side and see the left side. There's a lot of difference. There's totally woven side on the left side, and it is not so woven on the right side. Geopolymerization, again, for a minute, we'll come back here. Alkali cations such as sodium and potassium, aluminosilicate precursors, basically SiO2 and Al2O3, often derived from fly ash, metakaolin, or slag. And reaction, this is dissolution of silica and alumina in alkaline medium, which forms into polycondensation, and ultimately gel formation will occur. And this reaction, what we call as sodium aluminosilicate hydrate, that what we popularly known as NaSH gel. What is the benefit of this? The benefit of this is a very low CO2 footprint compared to Portland cement. As we have seen, maximum is 400 kgs of carbon dioxide per ton, and excellent resistance to fire, acid, and sulfate attacks. Particularly, geopolymerization cements or the concrete are applicable where you have the industry where sulfates and other things are occurring, and also on the seashore where you have a lot of problems of the nature, particularly Bombay side and even other Madras and other things where the structure cannot stand more than 30 or 40 years because of these acid and sulfate attacks. And utilization of industrial byproducts, fly ash and slag. Fly ash, all we know that comes from the power plants. Slag comes from the steel plant. They are sustainable. And if you see here, the microstructure, this is actually SEM one. If you see the left side and the right side, unreacted fly ash particles, you could see the arrows, you could see the cracks, you could see the voids. Whereas on the other side, after reaction, NaSH, you don't find any type of crack, any type of void. That hope you can see, and you can, this is the microstructure at SEM level. And hydration. Hydration, always we can find out in ordinary Portland cement. And the inputs are calcium oxide and silica from clinker phases, water as the reaction medium, and hydration of clinker materials gives rise to precipitation of binding phases. The products are CSH gel, that is calcium silicate hydrate, and minor Portland-like, and benefits are well established, predictable performance, strong early age strength, and then compatible with existing construction practices. It is a consistent, we have been using for the last 40, 50 years, and India is king in manufacturing the cement across the country, across the world rather. And then if you can see this hydration, you can see the pores. Pores, you can see CSH, you can see, and then, but you have the pores. You can visualize these pores. And, but here, whether you can see the needles, lot of needles and reticular network like this is CSH is calcium silicate hydrate. The phases in ordinary Portland cement or rather advantageous, and whether the hydration has occurred or not, that can be seen because of these needles. When the needles you can see in the microstructure means hydration has occurred. And if you see the difference between cash and CSH, cash and CSH. Cash is basically from the geopolymer material, and CSH is basically from the Portland cement. If you could see the right side, you see the right side first, you could see nanosilica, small components, and violet color. On the left side, you don't have. And this is basically on the left side, you can see calcinated clay. And on the right side, you can see nano silicon dioxide. Nano silicon dioxide, that is basically CSH. And on the left side, we have calcinated clay. And this will result in the cash on the left side, CSH, Portland cement on the right side. And here, the comparison, you can see that to strength contribution is very high for CSH. OPC definitely is very having very good strength. Whereas cash, we are referring to cash, not geopolymerized one, basically with the one part where it's a binder. It's basically what we call as a hybrid binder. The hybrid binder, if you can go for, definitely the strength is also very good. And the chemical resistance of the ordinary Portland cement is moderate. And whereas cash, that is sulfate resistant, this is what we call slag cement. Cash is nothing but what we refer commonly as slag cement. Co-products CH, that is weak and leachable, and whereas on the right side you can see cash, minimal CH, more stable phases. Pore structure, if you have seen the things, larger pores, more connectivity. Here, denser and finer pores are you can see in the cash. Durability, vulnerable to carbonation and sulfate, and whereas cash, the slag cement is generally more durable and but depends on activator chemistry. What activation you are doing, what type of chemicals you are using. Here, role of precursors. Here, it's a very important. What is the role of precursors? There are two types of precursors. One is, you can see in the blue color, source precursor. Source precursor is basically the ingredient in the geopolymer, like in the slag cement. And activator precursor is actually a catalyst or a solvent to start the reaction and form a final product in geopolymer based products. Waste valorization, that's basically waste combustion, you can see. What are the challenges? Challenges are variability, reprocessing, and the needs. Variability, we will see the microstructures or the SEM photographs from slag or the fly ash from a different industries are different in nature. Maybe the same industry, maybe it's a iron steel plant. The steel plant of different regions may have different slags, and similarly fly ash from different industries will have different compositions. What is the role of activators? Activators are basically sodium hydroxide and sodium silicate. And environmental, you can see this. These are for the geopolymerization. Geopolymerization to occur, you have the good role of activators is required, sodium hydroxide and sodium silicate. And this is costly when compared to the OPC or ordinary Portland cement. The activator is nothing but cement plus water. Cement plus water. Water doesn't cost anything, whereas here the activators would cost sodium hydroxide and sodium silicate. They are costlier. This is the only one that is a costly thing in geopolymer. geopolymer cement level. Environmental paradox, activators are energy sensitive. And then what are the research on sustainable activators? Yes, the previous presentation was talking about the things from the agro products. Yes, here also sustainable activators are required. Sustainable activators can replace the sodium hydroxide and sodium silicate. This is being done gradually. A lot of research has to be carried out. Rice husk ash, it is widely available in the Andhra Pradesh and Odisha and West Bengal and other parts of the country also. It's very available, including Punjab, Haryana also. And waste water glass, basically rice has ash-based water glass. And then mechanical properties. When you compare geopolymer cement with that of the OPC, ordinary Portland cement, this is either comparable or superior strength to OPC. What I am referring as for 50 megapascals, not 30, 40 megapascals. When I was young, we could see 30 megapascal compressive strength, but now gradually it is at 50 megapascals. High early strength, these geopolymers will give you very, very high early strength even when compared to the OPC. Flexural properties, higher deflection capacity. Definitely, these are having higher flexural properties, higher deflection capacities. And if you could see the differences from the traditional concrete and Portland cement concrete, just I will read out. You please see that one after the other. Binder is that geopolymer binder that is consists of aluminosilicate and alkaline activator. And in Portland cement, it's basically Portland cement. Main components in the geopolymer concrete are industry byproducts, fly ash and slag, and chemical activators, as we discussed earlier. And then Portland cement, limestone and clay and water. And hardening process, geopolymerization, which is a chemical reaction. It's hydration. Hydration is a chemical reaction with water. Environmental impact, significantly lower CO2 footprint, 80 to 90% less, and uses industrial waste, no high temperature calcination. Calcination is a very, very low, actually at 600 degrees centigrade it will occur. And whereas in the Portland cement, it occurs at about 1450 degrees centigrade. And high CO2 footprint due to energy intensive heating of limestone for the Portland cement. And durability is excellent for geopolymer concrete, excellent resistance to chemical, sulfate, and fire, low shrinkage, and high early strength. And basically Portland cement, you know that, susceptible to chemical and sulfate attacks. And whereas curing, here we hardly know anything about curing of the Portland cement. No curing is required, only except you may have be curing what we say roughly as a curing, watering, you can be doing it. But whereas geopolymer concrete has to be cured, and without cure also is available, and you have to cure for about 6 to 48 hours at 80 to 90 degrees centigrade with the ovens, hot air, etc., etc. You have to cure particularly to gain this polymerization to occur. This polymerization to occur, you have to heat it. And then binder, as we see that aluminosilicate source and alkaline activator is about 10 to 20%. This alkaline activator in the geopolymer concrete, that is the main cost of it. Whereas the Portland cement is 10 to 15%, and fine aggregates, sand, in both the cases, it is 25 to 35%. This is basically, I'm referring it to concrete mix. The concrete mix of the of the geopolymer concrete and Portland cement. This is the composition, and coarse aggregate in both the cases, it is 30 to 40%, and water you will be using in Portland cement. No water is required for the geopolymer concrete. Only you have to use the alkaline activator. So more or less they are same. Sand, gravel is the same. Only Portland cement is 10 to 15% of the entire quantity of the concrete. You will be using it, whereas in the geopolymer concrete, aluminosilicate is about 20 to 40%, and alkaline activator is 10 to 20%. And basically, I am not going much into the composition of the geopolymer binder composition. And now you can see geopolymer composition diagram, if you can see, and fly ash is about by weight percent, 70%, sand 7%, cement 9%, microspheres about 14%, and other small additives are 0.005%. And you will be adding alkaline activator for this to make polymerized geopolymer. Okay, and then the durability and fire resistance, they are very much superior to acids and sulfate attacks. Low permeability structure, excellent fire resistance, stable up to 1000 degrees centigrade. Sustainability and economics, and state-wise prospects of geopolymer raw materials in million tons per annum availability. If you can see, you can rank Maharashtra is very, very high. Next is Chhattisgarh. Next is Jharkhand. Next is Odisha, Andhra Pradesh. These are the many states you can see, right from Odisha, West Bengal, Andhra Pradesh, Telangana, Maharashtra, Chhattisgarh, and Uttar Pradesh, Jharkhand, Gujarat, Tamil Nadu, Karnataka, then Madhya Pradesh, Rajasthan. Across the country, we have this fly ash. We have the other things also. Blast furnace slag also you have, and you can see that 2030, 2030, 2020, 2030, and 2050. I have shown it by arrows. The 2020 on the first one is 2020, what is available, and 2020, what is available in 2030, what would be the future prospects in 2050. If you can see, in the fly ash, there is no reduction, almost same what is available in 2020 and 2030 and 2050, you have the same, because you are going for power generation with the coal. Yes, they are available. Only if there is any reduction, means we are going for some other fuels or solar or what and wind power generation. That's why we are having reduced at in 2050. Whereas blast furnace slag, you could see, of course, when compared to fly ash, blast furnace slag is very, very less. Compare one-tenth of that. Chhattisgarh, you will have more. Maharashtra, you have more. And Jharkhand, of course, you have a lot of steel plants are there. You are having this. And Gujarat is less. Tamil Nadu is less. Karnataka is very less. Rajasthan is almost negligible. So fly ash becomes the major constraint in geopolymers, and their availability is very much there even at 2050. Our government of India says that we have to avoid cement by 2070 by any cost. That is possible through by going through alternatives. Whether only the question arrives here whether it is sustainable or not. Here I will tell you a story of what started in 1994-95 of sustainable wood particle boards. Wood particle board is no, not wood particle board, wood-free particle board. Wood-free particle board, we wanted to do it in India. Experimentally, we started. This is started with a bagasse-based particle board in Maharashtra in the district called Sangli. It is called as Islampur. And there the plant was started with the name of EcoBoard. But within 10 years, the plant could not survive because of sustainability. What is sustainability? The bagasse which is being used at the time, available at the time, was no more available because it is diverted to cogeneration at the sugar plants itself. So whatever the material, bagasse, sugarcane waste that is available was made a raw material to cogeneration. That's why the material was not available both for the paper. Paper was generated or made from the bagasse, and similarly particle boards were made from the bagasse, but it is no more available. And one time you will laugh, the sugar cane per ton rate was 900 rupees. Bagasse, which comes after that, after taking out the sugar cane juice, 3,000 rupees a ton. So similarly, we are sure, of course, these kind of things will not happen, but the policies of the government should be there, or otherwise there is a lot of problem in this particular case. National outlook for geopolymer raw materials. Here, for on small break, I will take for a minute. Yes. National outlook. Overall, fly ash. Fly ash at 2020, it is available 200 to 250 million tons per annum. In 2030, it is 230 to 280, means there is no reduction at all. In 2050, also there is no reduction at all. And the peak will be at 2030 to 35. Then you may ask me why the fly ash may reduce. Yes, we are going for power generation from the non-conventional sources. That's why we may not be insisting on the fly ash. GGBS, that is the slag. Slag is always less wherever the steel plants are there. You will have that, but steel production is getting increased. So 2050 we can see 60 to 90 million tons per annum. So total potential of India, when both these sources combined, fly ash and GGBS, it is 2020 it is 225 to 285, and in 2050 it is 280 to 360 tons. Means India can emerge as a global geopolymer hub. This is, please try to underline this, and India can emerge as a global geopolymer hub in the world. And I will tell you here the true story of Andhra Pradesh, now it is in Telangana, and of Odisha, Talcher power plant. Talcher power plant and in Odisha, not power plant, it's a urea plant in Odisha, and Ramagundam urea plant, both actually based on the coal. It is German technology, first time in the world they have started it, but within few years they developed the problems. Both have to be closed down, and now both have started. Talcher urea plant, fertilizer plant, and they started, but they suffered for about 30 to 50 to 40 years because of there are inherent problems with the technology. So any technology, whenever we are taking it forward, we should check it out, both pros and cons. Environmental benefits. Environmental benefits of geopolymer cement would be 40 to 80% reduction in carbon emissions, supports circular economy, waste diversion from landfills. Previously, in Rajasthan, and in many plants, many fly ash plants, we were asking how to take out this fly ash. There was no answer. for fly ash dumping. Now there is a demand from everywhere across the country for fly ash. Once upon a time, it's a waste. It was used for landfills and all that. Now, nowhere in one particular plant, what we asked is that 90% plus fly ash is used, means consumed, means there is no wastage. And they are all used not for landfills. They are all used for various purposes like this geopolymer cement. And life cycle assessment, activator paradox, sodium hydroxide and sodium silicate dominate footprint, and carbon intensity depends on electricity mix, and need for greener activators. As we have discussed, greener activators like rice husk, ash, these are the greener activators. And then economic viability, initially higher initial cost than OPC. The OPC, we have the technology, we have the know-how, we have the machinery, and everybody is trained in that. And OPC is not a problem, but geopolymer cement has its own problems. You should invest more. And this what we have stating, these activators are also costly, like sodium hydroxide and sodium silicate and all that. They are all very costly. A lower life cycle cost due to durability. Durability is another thing which we have to see that. Economies of scale expected with wider adoption. Here, case study, life cycle economics. Unless and until you see the case study, you will not believe it. And you can make high performance concrete or M50 grade with geopolymer, which is cheaper than OPC. And it reduces repair and maintenance costs over service life. The things which are made with geopolymer concrete or the cement, they have reduced repair and maintenance cost over service life. Applications and case studies, I will show you some of the very interesting case studies here. Infrastructure applications, airports, highways, and precast units, bridges, marine structures, and durable solution for aggressive environments. And then innovative applications, geopolymer foams, they are fire resistant and they are used for insulation also. Because of the microstructure, I will show you the microstructure and wonderful microstructure where both they can be used for different applications. And one of them is fire resistant and another is insulation. And 3D printing for construction. Yes, 3D printing for construction, geopolymer concrete is a very much suitable. Bricks and masonry from industrial waste, that what we are doing it. Bricks and masonry from industrial waste, we are doing it. Wastewater treatment structure, we are making it. So you can see, this is porous geopolymer microstructure. Once again, porous geopolymer microstructure. This is of the geopolymer only, but you could see one is Gladstone, another is Torong, another is Augusta, another is Collie, another is Piper. And these are the microstructure. These fly ash obtained from different power plants in Australia. So the microstructure will be different because it will have the constituents of this geopolymer, this fly ash are different. Here you could see the bottom end, fly ash, very thin, silicon dioxide, alumina, and calcium oxide content. There are different things that are from the different plants. You have different compositions of silica and alumina and CO content. That's why the microstructure would differ. So it is not one and the same. Before doing the things batch to batch, you have to check it out from source to source. You have to check it out before using for the final application. So a lot of testing and research is necessary by selecting any by using any of these raw material. And microstructure type, as you see on the left side, and key features on the middle one, and what are the applications at the right side end. You see Nash gel, cash gel, hybrid gels, crystalline and unreacted particles and fillers. So you have different microstructure. Nash gel, for example, is used for high strength concrete and precast blocks. And cash gel, as we said, it's a hybrid one. It's a calcium aluminosilicate hydrate. It's used for rapid repair works. Wherever a road is broken, road has to be repaired, immediately cash gel concrete, you can use it because it rapid repair works, you can do that. And infrastructure needing fast setting also, through cash you can do it. Hybrid gels also can be used for large infrastructures and bridges, marine construction, and crystalline zeolite phases. This is very, very important. If you see that fire and heat resistant panels, you can use it. Thermal barriers, you can do it. And ion exchangers also, you can use it for the one that is crystalline zeolite phases. And you could see 3D printed geopolymer structure. A wonderful thing, 3D printed geopolymer structure. This you can do it. And another interesting case study is that in the Brisbane West Wellcamp Airport, they have built 40,000 cubic meters geopolymer concrete, which is used for aircraft pavements, runway, including the turning node and apron areas. These are the crucial area in the airport where heavy loads, dynamic loads are coming, shock loads are coming, where this particular geopolymer concrete is used. You can see this Brisbane West Wellcamp Airport in Australia. So the entire thing, whatever you are seeing over there, all the concrete, all the things are made by the geopolymer cement. And Collicrete project. What is Collicrete project? Collicrete is nothing but a fly ash from the fly ash based from the Collie power plant is used. This is a basically low calcium one. It is used. That's why it's called Collicrete project, where whatever the concrete that used from the Collie fly ash, they call as Collicrete project. And this is this particular one was used and it resulted in 80% of the reduction. And geopolymer applications in India, and research and academic, yes, we can do a lot of work, and IIT Indore is doing a lot of work. Infrastructure and road, and of course in India it has to pick up. Only in Chhattisgarh, only half a kilometer road of geopolymer road was made, and Delhi Metro pilot plant was done. A small work pilot thing was done. Housing and sanitation, Swachh Bharat machine. Yes, they are building the toilets with this geoconcrete, and then industrial waste utilization, conversion of fly ash and then slag and red mud into binders. They are using it, and public and commercial Indian Railways is using testing sleepers. Sleepers, another area with the JSW cement, geopolymer based products, And environmental benefits, there, as you know, there are a lot of environmental benefits as CO2. CO2 releases into the atmosphere are reduced more than 60 to 80%. And here, of course, we are running out of time. But before that, I can tell you about the TRIS and inventive problem solving. TRIS is nothing but the inventive problem solving. It is a Russian acronym, and how that can be implemented here. Here, I will tell you before concluding. I may take additional 5 to 10 minutes. Sir, the coordinator, please allow me for another 10 minutes more up to 9:10 to finish off this particular small topic, which is very, very interesting. Actually, I have not included much initially, but I included later on. Here, in the contradiction, I will tell you, in the daily life, we want our car to give more mileage. Our car to give more mileage means its weight should be less. If the weight is less, the problem is its stability is lost. So what you want, mileage you want, but the problem that is coming is that stability. So in mechanical engineering, there are 39 contradictions. 39. One, you want to increase, automatically other is getting affected. So how to solve? Will you compromise? So Altshuler, a Russian scientist called Altshuler, has derived this particular thing, and he has gone through millions of patents for several years and find out in the entire mechanical engineering, and of course in civil engineering also these can be used, in biology they can be used, but the parameters are different, but civil and mechanical, all these parameters would fit. And the civil engineers, why I am presenting this particular topic to you is, you will go through what is there in the TRIS, and you will write a beautiful papers out of this particular TRIS. So to solve this contradiction, to solve this 39 by 39 contradiction, they have proposed 40 inventive principles. 40 inventive principles. So that inventive principles, if you can address, you can do it. That also he made as a table. Made as a table of 39 by 39, and then you can see this. I will tell you before going into that. A specific problem, you have a specific problem, convert them into general problem, then general problem, and then you give the general solution. From general solution, you go to the specific solution. This is basically TRIS problem solution process. So you are starting with specific problem and is solve for as a general problem, then convert into general problem and give the general solution. From general solution, you go to the specific solution. This is all the TRIS is. Here he gives 5 levels of problem solutions based on a patent literature. As I told you, Altshuler has gone through millions of patents. He found out that there are 5 types of patents. One is routine design, means a chair is there, a bench is there, which is actually of 2-seater. You want to make it as a 3-seater. So that the modification is done. That is 30%. Minor corrections to the existing system, instead of a wood, you can go for a particle board. That's a minor correction is done. That is basically level 2. Level 2 is basically 45%. So the first 2 things, routine design and minor correction, most of our engineers are making 75%. There's nothing called innovative there. So level 1 and level 2 either routine design, solutions or minor corrections, or we are making only 75. But fundamental improvements to an existing system which resolve contradictions within the industry, they are 20%. And solutions based on application of new scientific principles to perform primary functions of the design, they are 4%. Then pioneering innovations based on rare scientific discovery, like James Watt of steam engine, Alexander Graham Bell of telephone. These are the called inventions. So through TRIZ, if you use TRIZ, I am guaranteeing, not I am guaranteeing, everybody guarantees you that your problems, you can solve the problems at a level 3 and level 4. This is basically an engineer is expected to do. Unfortunately, most of our engineers will do level 1 and level 2 only. Here, okay, because I had to deal with more subject here. So here, whatever the parameters, contradictions, what I am saying, 39, though I am writing them horizontally, they are 1 to 39. I am numbering 1 to 39 horizontally. They are what we are calling as worsening parameter, and improve parameter is on the vertical side. Same thing, 1, 1 is same, 2, 2 are same, 3, 3 are same. And whatever you want, first thing is you try to, as an engineer, what you do is identify what you want to improve. What you want to improve first. What is getting worse? What is getting worse? What I am told you, one thing initially was mileage, more mileage. Say that is something like X. And what is getting worse? Stability. That worsen, you that particular thing, say that is Y. X and Y, where X and Y, that matrix or row and column, you identify that. You just here, you can see here. Small things were written here. You may not understand. You may not, but see that the first one is weight of moving object. I am going into the vertical fashion, weight of stationary object. And third one is length of moving object and length of stationary object. These are 39 parameters. There are 39 parameters. The same parameters on the horizontal line. Weight of moving object, weight of stationary object. Third, length of moving object, length of stationary object. Likewise, 39. All the 39 on the horizontal, all the 39 on the vertical, they are one and the same. Only thing is, you identify first, for example, you want to do something, length of moving object you want to improve. You want to improve, means you want to reduce it. And then you are saying that when the length of the moving object you want to increase, for example, you want to increase, improving, you want to increase third, and weight of the moving object definitely will increase. That is 3-1. You just see 3-1. 3 improvement, that is on the vertical side, and 1 weight of the moving object. You can see a cell over there, a cell. It is giving small letters. It is given with a green color, 8, 15, 29, 34. 8, 15, 29, 34. These are the principles, inventive principles, 40 principles are there. He has suggested that what you want to improve, first identify what is getting affected from your just thinking, you know that. Then accordingly, you identify, for example, here, volume of stationary object, number 8. Number 8, that you want to improve. Volume of the stationary object, number 8. And I want, if the volume of the stationary object is increased, definitely what is getting affected? Length of the stationary object. Number 4. You see, 8 improvement and 4 worsening feature. So how to solve that? How to solve that? You could see inventive principles as 35, 8, 2 and 14. 35, 8 means these are the principles which were given that if you attack it. These 4 principles. We have suggested these are the principles. Very clearly means for solving any engineering problem, I can say in mechanical and civil, you go through the theory of inventive problem solving, TRIZ, and you will solve the problems in a much better manner. You will get publications, you will get the solutions, and you will have a satisfaction. And whatever the things, outcome that is you are giving, it is not rudimentary engineering you are doing. You are all inventive problem solving, you will be doing it. I will tell you. Of course, here I am skipping here certain things. So, for example, here an example is given. That is, you can see an object is given which has not a regular shape. I want to put it in a the workpiece is there. I want to put it in a fixer. I want to fix it, and actually you cannot do that. So through this, it has suggested that placing multiple hard bushings around the workpiece would solve the problem. And that solution has come through this particular tris. And I will once more I will tell you. Many of you have taken the Coke tin. Coke tin was not a simple design by mechanical engineer or civil engineer. It was a wonderful design made through tris. It was a wonderful design. Coke tin has got a unique thing, and it was done through tris. Here we are interested in key contradiction in geopolymers. We want benefit, waste valorization, and low CO2. And we want waste to be utilized and low CO2 to be produced. Drawback. What is the drawback here? Benefit, we want to see the benefit. What is the drawback here? Is the high cost and high carbon activators. And if you try to solve through the tris, you want to get the benefit, that waste utilization and low CO2, you want to achieve it, but the drawback is high cost and high carbon activators. TRIM reframes this entire problem that aim for binder that is both low cost and low carbon. So what it gives a solution is that aim for binder that is low cost and low carbon. You need not think. Only thing is what benefit you expect, what drawback you are expecting. You in the TRIS matrix you identify. Automatically it will give you the solution. Here the TRIS principles are applied. 1 to 40, segmentation, anti-weight, nested dolls, preliminary, anti-action. Like this, 4 principles are applied. And similarly, another example is lightweight geopolymer foams. Anti-weight principle is applied, reduced density but high fire resistance, and applications in panels and insulation. For example, anti-weight principle, lightweight polymer foams, you want to do it. Here, reduced density but high fire resistance you want. So applications applications are in panels and insulation. For example, likewise, several problems, day-to-day problems of geopolymer. See, I will tell you, wherever the materials are there, whenever you are taking a material, and a mechanical or civil, there are 2 things. In the darkest of the dark night, you can always rely on TRIZ and SB charts. performance indices, ASB charts, and theory of inventive problem solving. They are your best friends. Then will give you the best things without depending on somebody else. Okay, here I will tell you ASB charts. I am not going into that much. Another 2 minutes I will take. So here there are about 20 charts to 30 charts he has drawn. Ashby is an Australian scientist. He has drawn 20 or 30 charts, but has taken all the materials in the world. All the materials in the world. One of the chart is Young's modulus versus density. Young's modulus versus density. So if you see the metals on the right side on the top, you have metals because Young's modulus is higher and also density is higher. Whereas triangle geopolymers, density is higher, but Young's modulus is lower. But what you want, E by rho, you want E by rho. E by rho, perhaps geopolymer may be giving it. Not because something, because if you see Young's modulus is higher, but the density is also higher. E by rho will become lower, whereas E by rho for the geopolymer may be effective. Similarly, insulation versus strength. Insulation versus strength. If you see that insulation, that is strength on the vertical axis, and on the horizontal axis, you have the insulation. If you can see metals, yellow colored are the metals. They have strength, but they don't have insulation. Polymers, they have don't have the strength, but they have insulation. But in between, polymers are coming. If you can see that, the polymers are right, yellow color, the polymers are coming. So that would be the solution. So through Ashby charts, performance indices, Ashby charts, and TRIZ, contradictory matrix, you can get the wonderful results. And finally, what are the current challenges? Current challenges are precursor variability. And variability, as we said, precursor both for the additives and other things, which we have to do that, and to reduce the costs of the binder. And the supply chain competition versus this is SCMs are nothing but supplementary cementing materials. Supply chain competition with supplementary cementing materials. You need more and more materials, and a limited large scale activator production. Where to activate production, it should be in the large scale. And institutional regulatory barriers, as we said, most of this doesn't have standard codes and testing methods. And so we have to do the standardized codes and testing methods. Hesitancy among designers and regulators, whether we have to use it or not. And need for performance-based standards. And so we need performance-based standards we have to produce. And research trends in this is low carbon activators from agricultural waste, that what we have discussed, low carbon activators from agricultural waste like rice husk, and then 3D printed geopolymer structures. It is possible, which we can do it. Hybrid systems for multifunctional performance. So the last 1 or 2 slides, you can see the drivers here is geopolymers and alkali activated materials, the future of sustainable binders. OPC is polluting a lot. It is 5 to 8% of carbon dioxide it is giving globally. And so it can be replaced by industry byproducts of fly ash and slag and husk ash, rice husk ash. CO2 reduction is 40 to 80% is possible versus OPC, and strength of these geopolymers can be 50 to 70 megapascals. Durability, yes, acid, sulfate, and marine applications you can use, and fire and thermal stability up to 1000 degrees centigrade, and life cycle cost savings are there. And the way forward is develop performance-based codes, invest in low carbon activators, showcase pilot projects like what I have seen is, and Odisha also has got a project in this geopolymer paste, and integrate. I strongly recommend integrate TRIZ and ASHB methods for this particular process. So way forward is develop performance-based codes, invest in low carbon activators, showcase pilot projects, and integrate TRIZ and ASHB methods. So final recommendations are geopolymers are eco-friendly, durable, and versatile. Integration of TRIZ, performance index, and ASHB enables innovation. Collaborative research, codes and scaling needed, and the future diversified sustainable binder toolkit. These are the references. This is it has taken more than 1 hour and a half. I was given only 1.5 hours, and I've taken. Sorry for that. And if you have any questions, please ask me. Thank you. Thank you, one and all. Thank you for the opportunity for the MITS Rayagada. Thank you.
Thank you, sir. Thank you for your valuable time and enlightening session. It's really very much helpful for us, sir. Sir, I would like to request our participants, if anybody has any query, please.
Any questions from the participants? TRIZ and ASHB charts. I hope that many of you are not knowing. Yes or no?
Yes, sir.
So I request you all, it's not a mechanical thing. It's not a mechanical thing. It's a wonderful kit. You
Yes,
can
sir.
use it.
Definitely.
Any questions, please, sir? Any questions? Srinu. There was Srinu, it seems. My name is also Srinivas. Okay. Sharma. Okay. Shashawat Sharma. Any person from Maharashtra? Any person from Maharashtra? I think Prital Patil madam was there earlier.
Participants, please, you can turn on your microphones and ask your questions.
Murali Krishna.
Good evening, sir.
Good evening, Prital madam. How are you?
I am fine, sir. How are you?
Fine, madam.
Sir,
So-
actually, that geosynthetic material is used for the mechanical purpose or the civil purpose?
Madam, geopolymer is basically a cement substitute, as what we discussed.
Okay.
Okay. You are asking me why I am introducing TRIZ.
Yes, sir.
TRIZ,
Yes, sir.
see, means a computer. Computer is not for computer science students. It is for everyone.
Yes, sir.
TRIZ and performance index, and this ASPE charts is for everyone to use.
Yes, sir.
Whatever I have shown you, Brisbane Airport and cements and all that, you know,
Yes, sir.
all that is they're all cement substitutes.
Yes, sir.
Okay, you can.
So, what the formation of वो matrix है ना?
हाँ.
वो नहीं समझ में आया मुझे.
अच्छा, अब मैं भेज देता हूँ, आप देख लीजिए.
अच्छा, ठीक है. Okay, sir. Thank you.
Okay.
Thank you, ma'am, for your participation. Here, please, participants, please switch on your videos just for a quick screenshot. Thank you so much. Thank you. Thank you, sir.
Thank you.
Sites have enriched our faculty development program, and we truly appreciate your contribution, sir.
Right, sir. Thank you, madam. Thank you. Thank you, Arnav. Thank you.
Thank you. With that, we come to the conclusion of today's session here. On behalf of the organizing team, I sincerely thank all the dignitaries, speakers, and participants for their valuable presence and contribution. We look forward to your continued support and active participation for tomorrow's program. Wishing you all a pleasant evening. Thank you so much.
Thank you.